Hi everyone, welcome to Go Classes. Please tell me, is the audio clear? Am I audible? Let me know. Please tell me, am I audible? Is the audio, video, is everything fine? Let me know. So, in this session, we are going to discuss All India Mock Test 3 for GATE Computer Science 2024. The solutions of this All India Mock Test 3, Part 1. This is what we are going to discuss in this lecture. Okay. Remember, for all the All India Mock Test, the solutions you can find in this playlist. Okay, so if you want All India Mock Test 2 solutions, All India Mock Test 1 solutions, also All India Mock Test 3 solutions, all the part, they will be available in this playlist. Okay, so on the Go Classes YouTube channel, you can search Go Classes test quiz. You can search this on the YouTube. You can search this. Okay, then you can go to this playlist. You can go. You can join. You can see. Okay, you can visit this playlist. Go Classes test quizzes homework discussion. Okay, in this playlist, basically, we are discussing all the All India mock test. Okay, all the All India mock test solutions, all the parts you will find in this playlist. So you can just check it out. Okay, now let's start this session now. So let's start with this question. This is a very easy question. Consider the following NFA, this non-deterministic finite automata that is given to you. Consider the following NFA M and say what language is recognized by constructing the machine that recognizes the complement of LM in A star. So very simple question. So first of all, the question is asking that this machine is given to you, this NFA N is given to you. This is your NFA M. And the question is asking the complement of LM. The question is asking that first you find what is LM. Okay, from this NFA, you find what is the language accepted by this NFA. And then you find what is LM complement. Okay, the complement of LM we need to find. We need to find the complement of LM in A star. What that means? That means your alphabet is simply A. Your alphabet is simply A. This is your alphabet. Okay. So the question is asking, say what language is recognized by constructing the machine that recognizes complement of LM. Okay. So very simple question, right? What is LM? In this question, what is the language? You can see LM. What is the language that is recognized by this given NFA? So you can see that is any number of A's followed by A. Okay. Any number of A can come. And then finally, at last, you should have A, and then you will go to the final state. In the final state, you cannot read any symbol. So very simple. The language is basically A star A. That is same as A plus. Okay. So this is the language. Now, what is the language complement? What is the LM complement here? You can see your alphabet is basically A. So you can see sigma star. I can say the set of all strings, that is basically your A star. That is basically A star. Okay. So you can easily see the complement of LM, that is going to be only this string, only the empty string. You can see this given NFA does not accept empty string. It is accepting all other strings. Okay, every non-empty string is accepted by the given NFA. So you can see the complement of the language of this NFA, that will be set containing empty string. So you can see this will be LM complement set containing empty string. The answer will be option D. Okay, is this clear? Let me know. So very simple question. Now what are the silly mistakes some students made? What do you think? The silly mistake, let me tell you the common mistake. A silly mistake that some students have made in this question. A silly mistake that some students have made in this question, that is basically they have complemented the NFA. See, the question is asking complement of LM. The question is asking that you find LM, what is the language of this NFA, and then you find the complement. Okay. So first you find the language of this NFA and then you find the complement of that language. This is what question is asking. But some students, what they have done this silly mistake. Let me tell you the silly mistake. The silly mistake is like this. they have created complement of states. They have complemented the states. You can see this non-final state, they made it final, and this final state, they made it non-final, right? Okay, so you can see basically they have complemented the states. They have complemented the states. So if you complement the states, okay, this was your NFA M. So basically what students have done, some students what they have done, they have complemented the states, or I can say they have complemented the NFA, the states of the NFA, they have complemented. Okay, then you can easily see that they are getting this, the language that they are getting, that will be A star. Okay, then this is the silly mistake. So option B is the silly mistake. Silly mistake is option B. Silly mistake is option B. Okay, so remember, the question is asking the complement of the language. The question is not asking that you complement the states of the NFA. This NFA is given to you. The question is not saying that you complement the states of this NFA. The question is simply saying that you find the complement of the language that is recognized by this NFA. Okay, so very simple question for 1 mark. Now let's move on. Now let's solve this question. A context-free grammar is given to you. The S is the start symbol. The terminals are given to you, that is A, semicolon, less than, greater than. So these symbols, these are the terminals. S, L, R, these are the non-terminals. S is the start symbol. This context-free grammar you have. How many different parse tree are there for this string? For this string, how many different parse tree are there? So let's solve it. So let's parse this string. You have this string. Let me first write the grammar. So you can see that grammar is basically less than L. S, you can replace this S, this start variable, you can replace with less than L, or you can replace with A. Similarly, this L you can replace with this L. You can replace with AR, or you can replace with less than LR. Okay. Then you can see R. This R you can replace with greater than, or this symbol. Okay, so you can see that this is what you can do. Just give me a second. Okay, so this is the grammar that is given to you. You can easily see. Now, how many different parse tree? This string, the question is talking about this string, that is this symbol, then finally A, then this greater symbol, then semicolon, then A, then this greater symbol, and then, yeah, okay, so this is the string. So this is just a question mark. This is not a terminal. Okay, this is just a question mark. This is just for the question mark, like this. Okay, the string is basically this. This is your string. This is the string W. Okay, now let's see what will be the answer for this question. So let's try to parse this string that is given to you. Very simple. The start variable, that is S. This is the start variable. From the start variable, tell me which production you will take. The production number 1 or the production number 2. This start variable I can replace with less than L, or I can replace with A. You can see if you want this string, then definitely the only choice is to take this. Yes or no? We need to use this production. So very simple. This is the only choice. There is no other choice. Right now we don't have any other choice. Yes or no? Okay. So you can see, because this is the string we want. Now remember, this we have got. This symbol, you can see this symbol we have got. Okay, we have got this symbol already. Now what we need to do? We need to create this from L. Okay, with this L we need to create this string. Now tell me what we need to do. Now what the next thing to do? You can see. So this L you can replace with AR, or you can replace with less than LR. Okay, but you can see the next symbol I want is less than. Yes or no? I want the next symbol that is less than. This is the symbol I want. So what I will do? I will replace this L with less than R. There is no other choice. I don't have any other choice. Now you can see this symbol also we got. Okay, we got this symbol also. So now what we need to do? With this LR, with the help of this LR, we need to create this string. Okay, we have already created these two symbols. Now we need to create this string a greater, then semicolon a greater. Okay, so let's see this L I can replace with what? I want the next symbol, that is a. I want next symbol, I want, that is a. So should I take this production or should I take this production? Very simple, I should take the first production. So very simple, this I will replace with AR. There is no other choice. Now I got the A also. So you can see these three symbols I already got. Now we need to create this much string. This is the remaining string. So very simple. Now with this R, what I can do? With this R either I can replace with greater symbol or I can replace with this symbol. So you can see I want the next symbol, that is greater. So what I will do, I will replace this with greater. Okay, this production I will use the first production of R. That is what I am going to use. Okay, after that we need to create this much string. So you can see I want semicolon. Okay, so this R I can replace with semicolon L. Okay, this R I can replace with semicolon L. Very simple. Now this semicolon also we got this semicolon also. So these are the things that we got. Now you can see, now with the help of this L, I need to create a greater. Okay, I need to create a greater. So you can see I want the next symbol, that is a. So I will use this production. Okay, very simple, I will use this production. Okay, so this L I will replace with AR. Now I got this A also. Now finally what I will do, I need this greater symbol. So R I will replace with greater symbol. Okay, R I will replace with greater symbol. So you can easily see there is only one parse tree possible. Yes or no? For this string W, there is only one parse tree possible because there is no choice. We don't have any choice. So for this W, there is only one parse tree. Only one parse tree possible. Okay, so very simple. For this question, the answer is going to be 1. Now let me tell you, actually, look at this grammar. This grammar is actually, if you notice, this is actually LL1 grammar. Yes or no? Look at this grammar. The grammar is like this. S you can replace with less than L, or you can replace with A. L you can replace with AR, or you can replace with LR. Okay, sorry, less than LR. Now next you can see R you can replace with greater, or you can replace like this. Okay, or you can replace with this. So very simple. Now look at this grammar and tell me, this grammar, if you notice, this is actually LL1 grammar. Okay, this is actually LL1 grammar. In the compiler design you study the something concept called LL1 grammar. Yes or no? So you can see this is actually LL1 grammar, because what you can see, there is no ambiguity here, right? For example, in the string, please notice. In the string, if the first symbol is this, then there is no ambiguity. You have to take this production. Yes or no? Basically, there is no ambiguity between these two productions. Okay, which production to use, this production or this production, there is no ambiguity. Okay, because if the next symbol in the string is less than, then you will use this production. Yes or no? And you can see if the next symbol is A, then you will use this production. So very simple, there is no ambiguity. Okay, if the next symbol is this, then you will use this production. Okay, or if the next symbol is A, you will use this production. Similarly, you can notice in L, if the next symbol is, let's assume A, then you will use this production. If the next symbol is less than, then you will use this production. So again, there is no ambiguity. Next, you can see in R also the same thing. If the next symbol is this, then you will use this production. If the next symbol is this, you will use this production. Okay, so again, you can see there is no ambiguity. So this grammar, if you notice, this is actually LL1 grammar. There is no ambiguity for any non-terminal. Okay, for any non-terminal, there is no ambiguity which production to choose. So if I give you some string, then remember, if you are at any non-terminal, then what you can do, you can uniquely decide without any ambiguity, you can decide which next production to choose. So you can easily see that for any non-terminal, there is no ambiguity which production to choose. Yes or no? Everything is very clear. Just see what the next symbol you want. In the string, what is the next symbol you want? Just look at that next symbol and you can easily decide which production to choose from any non-terminal. Okay, for example, let's assume the next symbol, let's assume this next symbol is, let's assume this. And let's assume I am at this terminal L. I am at this non-terminal. Okay, so you can easily see I will use this production. So there is no ambiguity. So that is the reason I can say that this grammar, because this is LL1, and every LL1 grammar is unambiguous. Yes or no? Every LL1 grammar is actually unambiguous. Okay, so because it is unambiguous grammar, so for any string which belongs to the language of this grammar, that will have only one parse tree. Yes or no? Okay, any string which belongs to the language of this grammar, that will have only one parse tree. Okay. So let me see if anyone has any doubt. A student is asking, in the previous question, why don't we have phi in the previous question? So let me just answer that doubt. See, in this question, the question is asking the complement of LM. Okay, first you find what is LM. First you find what is L of M. You can see all the strings which are of A plus, these strings are accepted. Yes or no? You can see any number of A can come. Okay, this simply means A star. So you can see any number of A can come. In this state, any number of A can come, and then you can see, and after any number of A, the last symbol should be A. Yes or no? The last symbol should be A. So you can see any number of A can come, any number of A can come, then the last symbol must be A. So this is actually A plus, this is LM. Okay, so your LM, if you notice, that is actually A plus, means A, double A, triple A, and so on. So in the complement, in the LM complement, what will be the string? Very simple. The only string which does not belong to LM, that is empty string. Yes or no? Empty string is the only string that does not belong to the LM. Okay, correct. Because you can see the question is already saying that your sigma star is A star. Your sigma star is basically A star. So you can easily see that the only string which does not belong to the language, that is empty string. Okay, is this clear? Chinte Beda, is your doubt clear? Let me know. Okay. So let's move on now. Is this question clear to everyone? The given grammar is LL1. Every LL1 grammar is always unambiguous. So you can see any string which belongs to the language of this grammar, any string which can be generated by this grammar will only have one parse tree. Okay, yes or no? Will have a unique parse tree. So the answer for this question will be 1. Now let's solve this question. This is a nice question, a beautiful question. The number of ways that one can divide 10 distinguishable objects into 3 indistinguishable non-empty piles, that is already given to you. You don't have to calculate. So you can see 10 distinguishable objects, 10 objects which are distinguishable means they are different. Distinguishable means they are basically different objects. All the objects, they are different. Okay. And the piles, they are indistinguishable. Indistinguishable means identical. That means identical. Okay. Now the question is saying that how many ways are there to divide 10 different objects into 3 identical non-empty piles? That is already given to you. You don't have to calculate. Now the question is saying how many different ways are there to do this if the piles are distinguishable. If the piles are distinguishable. See, this is a beautiful question. Let me tell you why. This is a beautiful question because it is talking about the relationship between two templates of distribution. See, distribution has, when you distribute objects into boxes, then there are some templates. Yes or no? When we distribute objects into boxes, then there are total 4 templates are there. The first template, that is distinguishable objects, distinguishable boxes, different objects, different boxes. Yes or no? All the objects are different and all the boxes are different. The another template is basically DOIB, that is different objects, identical boxes, or I can say the next template, the second template I can say that is IODB. Okay, identical objects and different boxes. The third template I can say that is DOIB, different objects, identical boxes. Boxes are same, identical boxes but different objects. And the last template is basically IOIB. Now this question is basically talking about the relationship between these two templates. One template is distinguishable object, indistinguishable boxes. Okay, distinguishable objects. So you can see this template, the relationship between, what is the relationship between this template and this template? Yes or no? So basically the relationship This question is related to the relationship between these two. Yes or no? Between these two templates. Okay. So now let's see what are the relationship between these two templates. So you can easily see one thing. So you have total 10 distinguishable objects you have. Okay. So the objects, remember the objects are already distinguishable. So there are total 10 objects. Let me call them A, B, C, D, E, F, G, H. Just to explain, I am explaining. That is the reason I am taking this entire example. So you can see there are total 10 objects and there are boxes also. And there are boxes. Okay. The boxes are identical. Initially, you can see the boxes are identical. Okay. So all the three boxes, these are identical. So let me call them capital B, or maybe let me call them capital R, capital R, capital R. Okay. All the three boxes are identical. Now you can easily see in this situation, what is the answer? In this situation, the answer is already given to you, as long as they must be non-empty. Okay, at least one person here, at least one person here, at least one person here. Okay, they must be non-empty. They must be non-empty. You cannot keep them empty. So they must be non-empty. This is already given to you. Now, so if you have these distinguishable different objects and three identical boxes, which you need to keep them non-empty. Okay, means at least one object must go to every box. Every box must have at least one object. Okay, so every box must be non-empty. So in this situation, the answer is already given to you, that is 9330. 9330. Now the question is saying that if we make boxes distinguishable, then what will happen? Okay, now this is what we are doing. We are making the boxes distinguishable. Now let me tell you what will happen. See, look at the relationship between these two. Okay, now what is going to happen? So let me tell you what will happen. So let me compare them side by side. Okay, let me compare them side by side. On one side I am putting this distinguishable objects, identical boxes. On another side I am putting DO, DB. Okay, so let me compare them side by side and you tell me what is the relationship between them. Okay, so let's see. First you tell me, in this DOIB means distinguishable object, identical boxes, R, all the boxes are same, and here all the boxes are different, R1, R2, R3. Now you notice one thing, that here you can notice, please tell me, in this situation you tell me, if I put AB here, if I put CDE here, and if I put FGHIJ here, now tell me, this setting and this setting, are they different? CDE here, AB here, FGHIJ here. These two settings, are they different? Please tell me. Are they different or same? I am asking this way and this way. These two distributions, are they same or different? These two distributions, let me know. Are they same or different? They are basically same. They are same ways. Okay, they are same ways because you can see all the boxes, they are same. All the boxes are identical. Okay, so remember, the boxes are identical. So there is no difference in the boxes. Basically, the only thing that matters is that AB is together, CDE is together, FGHIJ is together. Yes or no? So remember, these two are same ways. Is this clear? But you can notice, if I do like this, like for example, if I do like this AC here, and let's assume I do BDE together and I do FGHIJ, now they will be different. Okay, now these two will be different. Now these two will be different. Okay, now come back to this DODB. In this DODB, you tell me, they will be same or different? In the DODB, you tell me, they will be same or different? FGHIJ, this is CDE, AB, FGHIJ. Okay, in the DODB, now the rooms are different. Okay, you can see all the boxes are different. This may be big box, this is a small box, maybe this is a very big box. Okay, so you can easily see that these are different ways. Yes or no? Now these are different ways. So we have to calculate them differently. I hope you understood. Okay, now you tell me one thing. If I give you any answer here, then corresponding to that, how many answers I will get here? See, if I give you any answer here, for example, any distribution I give you here, in the case of DOIB, If I give you some distribution, consider this distribution A, B, C, D, E together, F, G, H, I, J together. Now tell me, corresponding to this distribution, how many distributions you will have if the boxes are different? Tell me, I am asking, corresponding to this distribution I am giving to you, when the boxes are same, when all the boxes are same, then what I am doing? A, B together, C, D, E together, F, G, H, I, J together. Yes or no? This is what I am doing. I am putting A, B together, C, D, E together, F, G, H, I, J together. This is what I am doing in the case of D, O, I, B. When the boxes are same, then this is the distribution that I have done. Now you tell me, if the boxes are different, then corresponding to this, how many distributions I will have? See, this is a single distribution, right? I can say this one distribution will have how many distributions in the DODB? That will be 3 factorial. Yes or no? Very good. That will be 3 factorial. R1, R2, R3. That is going to be 3 factorial. I hope you understood. Okay, so that is the point. That is the simple point. I hope you understood. So you can see, for example, you can put AB here, CDE here, and F to J here. Another distribution will be AB here, F to J here, CDE here. Another distribution can be F to J here, AB here, CDE here. Another distribution can be F to J here, CDE here, AB here. Another distribution can be CDE here, AB here, F to J here. Okay, another can be CDE here, F to J here, AB here. So this is what I am telling you, that you are going to get total 3 factorial distributions. Okay, you are going to get total 3 factorial distributions. This is what you are going to get. Okay, so remember, for every answer here, remember, if I give you some answer here, let me call it distribution D1. Okay, for this distribution D1, there will be total 3 factorial distributions here. Okay, there will be total 3 factorial distributions here. Is this clear? If I give you some distribution D2 here, there will be 3 factorial distributions here. If I give you some distribution D3 here, there will be 3 factorial distributions here. I hope you are getting my point. Okay, so tell me finally, how many distributions you have here? Already the question is already given to you, that you have 9330. These many distributions you have, 9330. So for this distribution, for this D9330, okay, for this D9330, like this, okay, this last distribution, I can say D last. For this D last also 3 factorial distributions will happen. Okay, so tell me total, what will be the answer for this DODB template? So for this DODB template, the answer is going to be, so finally your answer, that will be 9330 multiplied by 3 factorial, and that is your, you can just calculate what will be the answer. Okay, is this clear? You can do the calculation, what will be the answer. So the answer is 9330 multiplied by 6. This will be your answer. But actually this question is beautiful, because you should understand the relationship between this one, you can see DOIB, okay, and DODB. DOIB, this template DOIB and DODB. Between these two templates, the relationship between these two templates, that is given, basically that is what this question is asking. Yes or no? The relationship between these two templates, that is what this question is asking. I hope you understood. Please tell me, is this clear to everyone? Let me know. Is this point clear? Anyone has any doubt in this? Okay. See, one more thing. Why this non-empty is given? Can you tell me why this non-empty is given? So let me give you the generalization, but you tell me why this non-empty is given. See, very simple point. Please understand. This is the conclusion. I am giving you the conclusion. On one hand, so let's assume you have objects. Objects are different. Okay, you have distinguishable objects. All the objects are distinguishable. See, tell me why this non-empty is given. Can anyone tell me why this non-empty is given? This non-empty word, why that is given? See, objects are distinguishable. Let's assume you have total n objects. Okay, let's assume you have total n objects you have. Okay, now they are distinguishable. Now there are two situations, but before that, non-empty distribution. Okay, distribute such that each box non-empty, each box non-empty, each box non-empty, each box is non-empty. Is this clear? What we are going to do, we are going to distribute such that each box is non-empty, each box must be non-empty. Now in this situation, please understand, in this situation, remember DOIB. Okay, DOIB. So you have some boxes. Maybe let's assume these are the objects, and let's assume there are total R boxes. Okay, let's assume there are total R boxes. Now you can easily see in this DOIB what will happen. All these boxes, they are basically same. Yes or no? All these boxes, they are basically same boxes. And in this DODB what will happen? All the boxes are different. R1, R2 and so on RR. Okay. So now you can easily see, if I give you some distribution here corresponding to that, how many distributions I will get here? Tell me. If I give you some distribution D1, please tell me. If I give you some distribution D, then corresponding to that, how many distributions you will get here? Let me know. How many distributions you are going to get here? Tell me. So for this distribution D, if you have this distribution D, okay, or I can say this is your distribution D1. For this distribution D1, corresponding to this distribution D1, how many distributions you will have here? That will be R factorial. Yes or no? That is going to be R factorial. Is this clear? Similarly, for the next distribution, okay, for the next distribution D2 also you will have R factorial here. Is this clear? Please tell me. So like this, for every distribution, remember, for every distribution you are getting R factorial here. So like this, I hope you understood. Okay, so if your answer here, okay, remember, if your answer for DOIB, let's assume K, then what will be your answer for DODB? What will be your answer for DODB? Please tell me. If your answer for DOIB is K ways, okay, or I can say K distributions, or I can say total K distributions, then what will be your answer for DODB? That will be K multiplied by R factorial. Yes or no? Or I can say, so very simple, that will be K multiplied by R factorial. So this will be your answer. I hope you understood. Is this point clear? Because for every answer here, there will be R factorial answer here. Okay, for every distribution here, there will be R factorial distributions here. I hope this point is clear. So if the answer here is K, then answer here will be K into R factorial. But here this word is important, non-empty. This word is actually very important. Can anyone tell me why this word is important? Anyone? Why this word is important? Please tell me. This is my question. Why this word is important? This word, that all the boxes are non-empty. Okay. Why this? See, this is the conclusion. I have given you the conclusion, but in this conclusion, this word non-empty is important. That all the boxes are non-empty, that is important. Can anyone tell me why this is important? See, very simple point. Okay. See, this is my question. My question is, why this non-empty word given? Why non-empty boxes is important? Is important for this beautiful relationship. Okay. Why this non-empty boxes? Why this non-empty boxes is important for this beautiful relationship between, for this cute relationship between DOIB and DODB. Between DOIB and DODB. Please tell me. For this cute relationship, why this non-empty boxes is important? Can anyone tell me? If you allow empty, then this beautiful relationship will be disturbed. See, just allow empty. Okay, let me take one example. Let's assume you have total 5 objects. Let's assume you have total 5 objects. Okay, A, B, C, D, A, B, C, D, E, and let's assume you have total 3 boxes. Okay, you have total 3 boxes, and assume you allow empty. Assume we allow empty boxes. We are allowing empty boxes. Is this clear? This is what we are allowing. Now notice this cute relationship. Okay, this cute relationship will be gone. This cute relationship will be gone. What is the cute relationship? The cute relationship is like this. For every answer here, there will be R factorial answer here. For every distribution here, R factorial distribution here. For every way here, R factorial ways here. Yes or no? So here if you have K ways, then here K into R factorial ways. This is the cute relationship. I hope you are getting this point. Okay, is this clear? See what I am telling you. The cute relationship, did you understand? Okay, the cute relationship between these. So DOIB, DODB. The cute relationship is like this, that for every way here, if you have some way here, way 1, okay, way 1, then there will be total R factorial ways here. If you have total R boxes, okay, if you have total R non-empty boxes, if you have total R non-empty boxes, okay, so please understand this relationship. If you have total R non-empty boxes, okay, then for every way here, and let's assume you have total N distinguishable objects. Okay, distinguishable objects. Now you can easily see, for every way here, there are R factorial ways here. For every way here, there are R factorial ways here. So this is a cute, very nice, beautiful relationship that is going on. Okay, for every way, for way T here, there will be R factorial ways here. Okay, so this is the idea. I hope you got it. So very simple. Is this clear? Now you can see, if you allow empty, assume you allow empty boxes. Now you tell me, on one side I am giving you DOIB, on another side I am giving you DODB. Okay, on one side DOIB, on another side I am giving you DODB. Now you tell me, this cute relationship will be gone or not? 3 boxes, here R, and here R1, R2, R3, these are the boxes. Okay, see, now the cute relationship will be gone. You tell me one thing. For this answer, for example, let's assume AB together, C together, and DE together. Okay, for this answer here, for this distribution here, how many distributions here? Just tell me. Let me know. How many distributions here? Let me know. For this particular distribution of DOIB, how many distributions in the DODB? That will be 3 factorial. Yes or no? You will have total 3 factorial. Okay, yes or no? Agree with me? You will have total 3 factorial. You can create total 3 factorial. Like for example, you can create A, B, C, D, E. You can create A, B, D, E, C, and so on. You can create C, A, B, D, E. Okay, and so on. Right? Okay, so total 6 you can create. I hope you understood. So very simple. But now you notice, if you allow empty boxes, then in this situation, let's assume I am putting AB here. Let's assume I am putting all of them here. I am putting A, B, C, D, E here. Okay, this is what I am doing. Now corresponding to that, how many distributions here? Please tell me. Let me know. Yes, very good. Illuminati, very good. Ankit, very good. Ankit is saying non-empty है इसीलिए R factorial किया. Very good, very good. Okay. Similarly, Richie Forum is saying if they are non-empty, then we can do this. Yes, very good, very good. So this beautiful relationship that you have, but that will be disturbed if you allow empty boxes. Assume if you allow empty boxes, then in this situation you can see. Tell me, corresponding to this distribution means A, B, C, D, E, they are together. These 5 people, they are together. All of them, they are together. Corresponding to this distribution, how many distributions I have here? Do I have 6? No, I have only 3. Yes or no? I don't have 6. I only have 3. Either I can put all of them together like this, or I can put all of them together like this, or I can put all of them together like this. So now I don't have 6. I only have 3. Yes or no? I don't have 6. I only have 3. but here you have 6. Yes or no? Is this clear? So if you allow non-empty, because of non-empty boxes, so if you have non-empty boxes, then this beautiful number is coming 3 factorial every time. Yes or no? This beautiful number 3 factorial is coming every time. But if you allow empty boxes, if we allow empty boxes, then in this situation, this beautiful relationship is gone. I hope you understood. Please tell me, did you understand this complete analysis? Let me know. See, there is a purpose of this question. Did you understand the purpose of this question? What you need to learn from this question, did you understand? Solving the question, you can solve it. You can solve it by different method. But I am asking the purpose of this question. Did you understand the relationship between DOIB and DODB? The relationship between these two, and why non-empty boxes is important. They have a cute relationship. They are couples. They are in a very cute relationship. But there is a condition, terms and conditions. That is, they must have non-empty boxes. Something like that. Yes or no? So they have a cute relationship, but there is a condition. I am just telling you that why that condition is there. If you remove that condition, means if you allow empty boxes, then what is the problem? Okay, so for example, just one last example. Let's assume that you have AB here and CD together. Corresponding to this, how many ways here? Corresponding to this distribution, how many distributions you will have here? Let me know. How many distributions you will have here? Please tell me. Corresponding to this. So corresponding to this one. So you can see here how many you have. Here actually you have 6. Okay, again you will have 6. Now you can check, again you will have 3 factorial. Okay, again you will have 3 factorial. So you can see for this there will be 3 factorial, and if you have this one, for example, all of them together like A, B, C, D, E, all of them together, for this there will be 3 only. Okay, 3 ways. So that's it. So I hope you are getting the point. Okay, so now you can easily see that is the reason these empty boxes are given. Okay. Of course, if you increase the number of boxes, then you can create more such cases. Okay, more such different cases you can create. But anyway, now let's come back to this final point. So I hope you understood this. So final answer, let me know. That is final answer for this question, for this previous question. For this question, you can see the final answer will be 9330 multiplied by 3 factorial. Okay, that is the final answer. Okay, so let's move on now. Now let's solve this question. This is another simple question but very good question. The number of ways we can divide 10 distinguishable objects, 10 different objects into 3 indistinguishable non-empty piles. Non-empty piles, that is 9330, that is given to you. In how many ways you can do this? If the objects are also indistinguishable, if the objects are also identical, then in how many ways you can do this? Now let me tell you why I gave you this question. Okay. See, I gave you this question because some students will be thinking that there is a relationship between these also. Yes or no? See, in this question, I want to ask you the relationship between IOIB, identical objects, identical boxes, and DOIB. Okay, basically I want to ask you the relationship between these two. Yes or no? Is this clear? The relationship between these two. These two templates. That is the purpose of this question, right? So actually many students, what they will do, either they will multiply by 3 factorial or they will divide by 3 factorial. Basically they will try to do something. Yes or no? But actually there is no relationship. Okay. So this is the simple point, that actually there is no relationship. This IUIB, this has no relationship with anyone. Okay, this has no relationship with anyone. So actually let me tell you, there is no relationship. None exist. Okay. So basically you cannot use this fact. This is what I am telling you. Okay. See, this is the answer in case of DOIB. Okay, this DOIB answer, you cannot use it. We cannot use this answer to find out IOIB. To find out IOIB, we cannot use this DOIB. This answer we cannot use. There is no relationship between them. Okay, so you just have to separately solve this. Is this clear? You just have to separately solve this question. So very simple point. Remember, I hope you got my point, that see, some students, what they will do, okay, maybe they will be doing like this, some students will be doing like this, some students will multiply with 3 factorial, some will divide by 3 factorial. Basically, some kind of relationship they will try to create. Okay, but actually there is no relationship exist. Okay, this IOIB, this is a very, I can say, very simple, and you have to do manual calculation. Okay, in this case of IOIB, there is no other way. The only way is manual calculation. The only way is a manual step-by-step calculation. Okay, is this clear? The only way is manual calculation in the case of IOIB. So this identical objects, identical boxes, if this question comes, then remember, the only way is manual calculation. If there is a formula, that will be extremely complicated. Okay, if there is a formula that will be extremely complicated means this manual calculation will be easy than the formula. Okay, so that is the reason in this case you will never find that people are using formula. If someone is using formula, that is more complicated, or I can say that will take more time than the manual calculation. Okay, that is the reason in the GATE exam, if this question comes, IOIB template, if this question comes, then they will give you small data. They will give you small number of objects, small number of boxes. For example, here we have how many objects, how many boxes? You can see here we have 10 objects and 3 boxes. Yes or no? 10 objects, 3 boxes. So let's calculate. So finally I can say that you have total 10 objects, 10 identical objects. Yes or no? Because IOIB template, the question is saying that if all the objects are identical, already the boxes are identical, then in this situation what will be the answer? So you can see 10 identical objects. Okay, next what you have? 10 identical objects, you can call them AAA. Okay, all of them like this. So total 10 A's you have. Okay, total 10 A's you have. Next you have 3 boxes. Yes or no? 3 identical boxes. 3 identical boxes. And the question is saying you have to keep them non-empty. Okay, this non-empty word is also there. So you have to keep them non-empty. Remember, 3 non-empty. You have to make sure that they are non-empty. Okay, non-empty boxes. So this distribution, how many ways are there? Very simple. So just do step-by-step calculation. These are your boxes. Okay, these are your 3 boxes, R. Okay, so you just have to do manual calculation, remember. So you can just create cases. For example, if all the objects, okay, just go step by step. Okay, I am creating cases. Please notice, I am creating cases. Case 1, because remember, all the boxes are same. The boxes are like this, R. These are the boxes. Okay, and all the objects are also same. There are total 10 A's. Okay, so all the objects are same, all the boxes are same, everything is same. This is your IOIB template. This is the IOIB template. So in this template, always go step by step. The case 1, when all the objects, when basically you are using only one box. Okay, using only one box. Okay, you are using only one box. If you use only one box, then how many ways are there? Tell me. If you use only one box, this is the case 1. Case 1 is using only one box. You are using only one box. If you are using only one box, then what you need to do? How many ways are there in this case? If you are using only one box, I am using only one room, only one box I am using. So all the objects I will put in that box. Yes or no? All these objects I will put in this box. So there is only one way, because all the objects are same, all the boxes are same. Yes or no? All the boxes are same. You don't have to decide which box to choose. Yes or no? Okay, because all the boxes are already same. So you can see, if you use only one box, then there will be only one way. Okay, that way is basically like this, that all the 10 objects are going But you can see this case, in this case, two boxes are non-empty. See, in this case, two boxes are actually empty. Yes or no? In this case, two boxes empty. In this case, two boxes empty. But that is not allowed. That is not allowed. Yes or no? The question is saying that, so you can see this case we don't have to consider. Okay, two boxes will be empty. This case we don't have to consider. Okay, remember the question, but question is asking that every box should be non-empty. But the question is asking that every box be non-empty. Every box must be non-empty. Okay, so this case you cannot consider. Okay, so remember this case number 1, you cannot consider. And I think this will be a silly mistake, right? Did you make this silly mistake? This silly mistake is possible because the question is saying that all the boxes must be non-empty. Every box must be non-empty. I think this silly mistake is very much possible that you can consider this case, that using only one box. If you use only one box, then that will be one way. But you can see this case we don't have to consider because the question is saying that all the boxes must be non-empty. So we cannot consider this case. This case we cannot consider. So this case can give you silly mistake. Okay, now let's see when all the boxes. So you can easily see first what I can do. First I can do, this is what I can do. Notice there are total 10 A's. Please notice there are total how many? There are total 10 A's are there. Okay, this is what you have. And there are 3 boxes R. Okay, there are 3 boxes, right? Yes or no? Now what I need to do, I need to make them non-empty. So what I will do, first I will give them 1A. Yes or no? To keep them non-empty, what I will do, initially I give them AAA. Okay, yes or no? Is this clear? So this is what I will do initially. In the beginning, I will do this. That to every box I can give 1A. To every box I am giving 1A. Is this clear? Because I want to keep them non-empty. Is this clear? Every box must be non-empty. Every box, now every box is non-empty. Yes or no? Because what I am doing, to every box I am giving 1A. 1A to every box I am giving. So this is what you can do in the beginning. In the beginning you can do this, and then what you do, then distribute the remaining 7 A's. Then distribute remaining 7 A's. Then distribute remaining 7 A's. Remaining 7 A's. Is this clear? Please tell me, is this understood? Very simple point. All the boxes must be non-empty. So what I am doing, to every box I am giving 1A. To every box I am giving 1A to every box so that they are non-empty. Okay, because now you can notice now all of them are non-empty. Now every box is non-empty. So now you can just simply distribute the remaining 7 A's. Now let me distribute. I am distributing the remaining 7 A's. Okay, so 7 A's into 3 boxes. Okay, this is what I am going to do. 7 A's in 3 boxes. So one way, if you use only one box. Okay, if you use only one box. This is the case number 1. Using one box only. Okay, if you use only one box, then in this situation there is only one way. Yes or no? So there is only one way. There is only one way. All the 7 A's will go to that box. Okay, yes or no? All the 7 A's will go to that box. Remember, in this case, boxes are non-empty. Boxes are non-empty. Why? Boxes are non-empty because we have already given them 1A, 1A, 1A. These boxes are like children. You can consider them like children. Okay, so to all the child, we have already given, I can say these are like identical children. You can consider them identical children. Now, to every child, we have already given 1 chocolate. Yes or no? So you can see, now what I am doing, now for the remaining 7 A's, I am distributing the remaining 7 A's into these 3 boxes. Now these are the cases I can create. Case 1, using only one box. So all the 7 A's I can put in one box. So that is only one way. What the next? What is case 2? What the case 2? Case 2 is using 2 boxes. Yes or no? This is the case 2, that you are using 2 boxes. If you use 2 boxes, then how many ways are there? Very simple. You can do this distribution 6-1. Means 6 A's in one box, 1A in another box. You are only using 2 boxes, remember. So you can do 5-2. You can do 4, 3. Yes or no? Can I do 3, 4? Can I do 3, 4? No. They will be same because boxes are same. Yes or no? 4, 3, 3, 4, they will be same. They will be same because boxes are same, because all the boxes are already same, you can notice. So that is the reason you cannot do this. So again, very simple, there are only 3 ways. Okay, in this case there are 3 ways. Finally, what is the case 3? What is the case 3? The case 3 is using 3 boxes. This is the case 3, using 3 boxes. If you use 3 boxes, then how many are possible? Very simple. In one box, I can give 5, in one box 1, in one box 1. This is possible, right? Yes or no? What else is possible? What else is possible? 4 in one box, 2 in one box, 1 in one box. This is also possible. What else is possible? 3 in one box. Yes or no? 3 in one box, 3 in one box, 1 in one box. That is also possible. Is there something else possible? Yes, 3 in one box, 2 in one box, 2 in one box. That is also possible. Is there anything else possible? Please tell me. You can check it. There is nothing else possible, right? Okay. So you can just check it. That only these are the possibilities. Only these are the possibilities. So there will be 4 ways. So that's it. Now you can stop. Okay. Now what you can do? Now you can stop. So finally, 7 A's into 3 boxes. The answer will be 1 plus. So you can see in the case 1. In the case 1, there is 1 way. In the case 2, there are 3 ways. In the case 3, there are 4 ways. Okay. So the answer will be total 8 ways. Is this clear? Please tell me. Is this point clear to everyone? Let me know. Is this question clear to everyone? Okay. So actually in this question, the small trick is that if you have IUIB, you have to do it manually. Okay. Whenever you have this template, IUIB template, there is no other way. This IUIB, identical object, identical boxes, identical object, identical boxes. This template you always have to handle manually. Always solve manually. Manually in a step-by-step sequence. In a step-by-step sequence. So that you don't forget any case. Okay, so in a step-by-step sequence. So you have to do it manually. Okay, now let's move on now. Now let's solve this question. This is a group theory question, a very simple question. This star is a binary operation on the rational numbers. So the base set, that is set of rational numbers. The operation is basically like this. This is the definition of the operation. A star B is equal to A plus B plus 2AB. Which of the following are true? Star is commutative. There is a rational number, that is star identity, means there is an identity element. Every rational number has inverse. Okay. So these are the options. Now let's see. Let's check all of them one by one. So first of all, you can notice this operation that is given to you. You understand this operation. Okay. First of all, you understand this operation. Remember, your base set is set of rational numbers and the operation is star. And the question is saying that A star B, that is equal to A plus B plus 2AB. Okay, that is A plus B plus 2AB. Now you understand this operation first. Let's understand this operation. Tell me, if A is 2 and let's assume if B is, let's assume 3, then what will be the answer? 2 star 3, that will be 2 plus 3 plus 2 multiplied by 2 multiplied by 3. So you can see that value. What that value will be? Let me know. So you can see this is 12 plus 5, that is 17. Is this clear? For example, if you have 2 star minus 1, what that will be? That will be 2 plus minus 1 plus 2 into 2 into minus 1. So what that will be? You can see that this will be 1 and this is going to be minus 4. So that will be minus 3. I hope you are getting the point. Okay, so this is the idea. Now remember, the base set is rational numbers. So for example, you can take 1 by 2 also, or 1 by 3 also you can take. So this will be plus 1 by 3 plus 2 into 2 into 1 by 3. Okay, so this will be the answer. So very simple. So just understand the operation first. Now let's solve it. Is this commutative? The first option is this commutative? Is this commutative? For commutative, you need to check Can I say x star y is equal to y star x? Okay, this is what you need to check. This is what we need to check. Okay, so let's check. Just check it. So what will be x star y? Tell me. I can say what is going to be x star y and what will be y star x. Let's see. Are they same or not? So x star y, that will be x plus y plus 2xy, and y star x, that will be y plus x plus 2yx. And yes, they are same. Yes or no? X plus y plus 2xy, y plus x plus 2yx, they are basically same. So yes, this is commutative. So this will be commutative. Okay, so the commutative property is satisfied. Now, so the question is saying this, yes, this is true. What about the next one? What about the identity element? The question is saying there is an identity element. There is a rational number which is identity element. Okay, so let's see, is there any identity element? Is there any identity element? See, the definition of identity element is like this. E is identity element. When can I say E is identity element? When can I say E is identity element? If and only if for all elements x in the base set, which is Q. Okay, for all elements in the base set, what should happen? This should happen that E star x should be equal to x, and that should be equal to x star E. Okay, so this is the definition of identity element. Very simple, that for all the elements E star x should be equal to x, and that should be equal to x star E. This is the definition of identity element. Now let's apply. Okay, so assume there is a identity element. We need to find the identity element. So just assume, I am just assuming that there is a identity element is E. Okay, so assume that identity element is E. If E is the identity element, then what should happen? Then you can notice A star E, that should be equal to A. Then A star E should be equal to A. Okay, so now A star E, that is A plus E plus 2AE, that should be equal to E. Sorry, that should be equal to A. That should be equal to A. Okay, so if you assume that E is the identity element, then A star E should be equal to A. Okay, so you can see A star E, that is A plus E plus 2AE, that is equal to A. Now you can cancel it. So is there any value which will satisfy? Yes, E equal to 0 will satisfy. Yes or no? From here you can notice E equal to 0. Okay, E equal to 0 will satisfy this equation. So yes, this 0 is the identity element. For this operation, okay, for this operation you can notice E equal to 0. Identity element is 0 because you can easily see for any element x in the rational number, if you find out what is x star 0, that will be x plus 0 plus 2 into x into 0, and that will be same as x. So that is the property of identity element. Okay, that is the property of identity element. So you can see 0 is the identity element here. What about inverse element? What about inverse property? Can I say every element has inverse? Can I say every element has inverse? Please tell me. What about inverse? The question is talking about inverse. So can I say every element has inverse? Remember, what is the definition of A inverse? A inverse definition is like this, that A inverse star A will be equal to E, and that will be same as A star A inverse. Okay, this is the definition of inverse. This is the definition of inverse. So you can see A inverse. For element A, what is the inverse? That will have this property. A inverse star A, that will be E, that will be A star A inverse. Okay, so can I say every element has inverse? Can I say every element is inverse? Now, let's check. Okay, let me check. Assume inverse of A is x. Okay, just assume for a moment, assume that inverse of A is x. Now in this situation, what should happen? In this situation, A star x should be equal to identity element, which is 0. Identity element is 0. So now you tell me, if I do A star x, that should be equal to 0. Now A star x is A plus x plus 2ax. That should be equal to 0. From here, what is the value of x? From here you can notice the x is equal to minus A divided by 1 plus 2a. Is this clear? This is the value of x you will get. So can I say For every element, can I say x will exist? Can I say for every element this x will exist? Now there is a problem here. You can see, if you take, for example, a equal to minus 1 by 2, if you take a equal to minus 1 by 2, now what will happen? Now this denominator will become 0. Please notice, this will become 0. If a equal to minus 1 by 2, then basically your inverse will be what? Your inverse will be basically divided by 0. Yes or no? Is something like this. Is this clear? If you take x equal to minus 1 by 2, sorry, if you take a equal to minus 1 by 2, if I take a equal to minus 1 by 2, then you can notice that this denominator will become 0. This denominator will become 0. Okay, so if a equal to minus 1 by 2, then a inverse does not exist. I can say a inverse does not exist. So this is the simple question, that for this element, this is the only element, remember, for which inverse does not exist. So for this element, you can see a inverse does not exist. So that is the reason inverse property is not there. We don't have inverse property. So this is basically false. Okay, this is actually true. So the answer for this question will be 1 and 2nd only. The question is asking which statement is true. So answer will be 1 and 2nd. Okay, let's move on now. Let's solve this question. This is a simple question from theory of computation. Consider the given context-free language. This context-free language L1 is given to you. A power m, b power n, c power n. Basically any number of a followed by b power n, c power n, means number of b must be same as number of c. Okay. Which of the following choices of language L2 is context-free and ensures that L1 intersection L2 is not context-free? Okay, see, this is a beautiful question. You can see L1 is given to you, that is a power m, b power n, c power n, where n comma m, they are greater than equal to 0. And now the question is saying that which of the following choices of L2 is context free, which of them must be context free, and L1 intersection L2 is not context free. So there are two situations here. What the question is asking? The question is asking basically two things. First of all, that L1 must be CFL. Yes, sorry, L2 must be CFL. L2 must be CFL. And the second thing, L1 intersection L2 must be not CFL. So there are two things here. Please understand. There are two things here. One is that L1 must be CFL. Sorry, L2 must be CFL, and L1 intersection L2 must be not CFL. Okay. So you tell me, this option D you can reject. Option D I can reject. Yes or no? This option D I can reject very easily. What is the reason? I can reject this option D because this is not even CFL. This option D, this is not even CFL. I don't even have to check it. Please notice, I don't even have to check, is not even CFL. The question is asking for a CFL. L2 must be CFL. See, read the question. The question is already saying that which of the following choices of language L2 is context free. Of language L2 is context free and ensures that L1 and intersection L2 is not context free. So remember, this option D you can reject, because this is not even CFL. A power k, b power 2k, c power 3k. Okay, so this, sorry, a power k, b power 2k, c power 2k. Yes, this is not even CFL. This is actually CSL but not CFL. So you can reject this option. This option is automatically gone. Now let's see the remaining options. We only have to check the remaining options. You can see in the remaining options, L2 is actually CFL. Yes or no? L2 is actually CFL. Now let's see, L1 intersection L2 will be what? You find out what is L1 intersection L2. So L1 is already given to you, that is a power n, that is a power m, b power n, c power n, where n comma m greater than equal to 0. Okay, now let's see each option one by one. So what is the option number A? Option number A, that is L2 equal to a power k b power 2k, a power k b power 2k c power m. Okay, where k comma m are greater than equal to 0, where they are greater than equal to 0. Okay, now you tell me what will be their intersection. So see, this L2 is actually CFL. This is actually CFL because you can easily do this. This PDA, push down automata, can easily recognize the strings in L2. Okay, now you tell me. Now tell me. So this L2 is actually CFL. In this option A, L2 is actually CFL. Okay, now what will be L1 intersection L2? What will be the common strings? What will be the common string? Notice, in L1, they must be same. BC must be same. Yes or no? Number of B, number of C, they must be same. See, intersection means common part. What are the common strings? What are the common strings? Just focus on the common part. Means those strings which will belong here and they will belong here. Okay, so remember, here you will have those strings which will belong here also, here also. So you can notice, if this string belongs here, then number of B must be equal to number of C. So remember, number of B must be equal to number of C. Number of B must be equal to number of C. This and this, they must be same. Okay, this and this, they must be same. Now, if this string belongs to L1 intersection L2, then this string also belongs to L2. In L2, remember, number of B is double of number of A. So you can see, very simple point, this type of strings you have in L1 intersection L2, where you have A power something, A power P, B power double P, okay, B power 2P and C power 2P. So this is the L1 intersection L2. I hope you are getting. Okay, where P is greater than equal to 0. Okay, is this clear? So this will be your L1 intersection L2, because remember, we are checking what are the common strings. Means the strings which are here also and here also. So basically those strings which will satisfy this property and they will satisfy this property. So you can see, if some string belongs to L1 intersection L2, then that string must have number of B equal to number of C. Number of B must be equal to number of C, and number of B must be double of number of A. Number of B must be double of number of A. So very simple. So you can see this is actually not CFL. A power P, B power 2P, C power 2P. This is actually not CFL. This language is not CFL. So you can see L2 is CFL, but L1 intersection L2 is not CFL. So option A is correct answer. Okay, option A is a correct answer. What about option B? So remember, here I can say option A is the answer. Option A is one of the answer. Okay, what about option B? In option B, L2 is given to you, and that is ABC power K. ABC power K, where K is greater than equal to 0. This is actually regular. This language is actually regular. Every regular language is CFL. Every regular language is CFL. So this is CFL also. This language L2 is actually regular, right? What is this language? This is actually ABC whole star. This is actually ABC whole star. Yes or no? Okay, ABC, ABC. Okay, so you can see this is actually ABC whole star. Is this clear? This language L2 is actually regular. Every regular language is CFL. Now tell me, what are the intersection? What is L1 intersection L2? If you take the common strings, the strings which are common, there are only two strings common. One is empty string. Empty string is common. The another string is ABC. This is common. No other string is common. No other string is common. Only two strings are common, that is empty string, comma ABC. Now this is actually CFL because this is regular. This is finite. Every finite language is regular and every regular language is CFL. So this is actually CFL. But we want L1 intersection L2 should be not CFL. So this is not the answer. Option B is not the answer. Okay. What about option C? Option C is A power K, B power M, C power K. Okay, let's see option C. That is A power K, B power M, C power K. B power M, C power K, where K comma M greater than equal to 0. Okay, now you tell me what will be the common part. First of all, this is actually CFL. This is actually CFL. The push down automata can easily do this. You have to just check that number of A must be equal to number of C. So push down automata can actually do this. This is actually CFL. What will be the common part? L1 intersection L2. The common strings. Remember, intersection means common strings. Just find out what are the strings which are common in these two. Which strings will belong to L1 and L2. So you can see, if some string belongs to L1, then number of B must be equal to number of C. If some string belongs to L2, then number of A must be equal to number of C. So the common strings will be like this. The common strings will be, please understand, the common strings will be like this. A power P, B power C. Remember, the common string will be like this. If you have A power P, then remember, in the common string, number of C must be equal to number of A. Okay, so you can see C also must be C power P. Now you can see, the common string will have number of B equal to number of C, number of B equal to number of C. So P greater than equal to 0. So very simple. This is the L1 intersection L2 and this is not CFL. This is actually CSL, this is not CFL. So finally I can say that option C is also correct. So the answer for this question will be AC. What is the common mistake in this question? What is the silly mistake in this question? Please tell me. Which silly mistake is possible? What do you think? What do you think? What is the most common silly mistake? In this question, what is the most common silly mistake? The most common silly mistake is, some students, they do not read this, that L2 must be context free. That L2 must be context free. Many students made this silly mistake. Okay, let me write it here. The silly mistake is, if you are saying that answer is ACD, if you are saying answer is ACD, this is silly mistake. Why? This is silly mistake. Remember, this is mistake. The reason is, the question is asking L2 must be context free. L2 must be context free. Okay, so remember, in the option D, L2 is not CFL. L2 is not CFL. Okay, so please understand, there are two conditions. The first condition is L2 must be context free. L2 must be context free. The second condition, L1 intersection L2 must be not context free. There are two conditions here. So please check it. Okay, please keep it in mind. So please take care. Don't make silly mistake in the GATE exam. Now let's solve this question. This is the most beautiful question of this test. I hope you loved this question. This is a very interesting question. See, D is a DFA with n states. Okay, D is a DFA with n states. N is a NFA with n states. Which of the following is or are true? The first option is saying, if D accepts some string of length n, then language of D is infinite. Okay. The next option, if D accept some string of length n minus 1, then language of D will be infinite. Let me first check the option number B. Okay. Because if B is true, then automatically A will be true. If option B is true, then automatically option A will be true. So let me check option number B. Option number B, that is, if DFA accept some string of length n minus 1, then the language will be infinite. Okay, let me check option number B. And this is very interesting question. Okay, option number B is like this. You have a DFA D. Okay, you have a DFA D. And this DFA D with n states. There are n states. The question is saying that it has total n states. Now, if D accept some string, okay, at least one string, some string of length n minus 1, then what you can say? Then can you guarantee? Then can we guarantee that language will be infinite? Then can we guarantee that language will be infinite? L of D will be infinite? What do you think? Can you guarantee? If DFA D accept some string of length n minus 1, where n is the number of states, then in this situation, can you guarantee that L will be infinite? And the answer is yes. The answer is yes, you can guarantee that language will be actually infinite. Let me prove it to you. Okay, so let's prove it. Now let me give you the proof. The proof is actually very easy. See, let's assume DFA. Okay, see, DFA is there, right? There is a DFA D. Okay, and this has total n states. So for a moment, let me write, let's assume that you have 4 states. Okay, I am assuming that you have total of 4 states. And this DFA accepts, let's assume this DFA accepts, just assume that this DFA accepts W equal to some string W equal to ABA. You can see length is n minus 1. Is this clear? Basically, the number of states is n, the number of states is n, and this is accepting this string A1, A2 and so on, an minus 1. Okay, this string is accepted. Is this clear? So let's assume that this is accepting this string. Now you tell me, can you guarantee that the language will be infinite? The language will be infinite? Yes, you can guarantee. See, notice one thing. Okay, let's try to make sure that there is no loop. Try to make sure that there is no loop. There is no loop in DFA from initial state to any final state. From initial state to any final state. Okay, from initial state to any final state. Okay, because remember, the language will be infinite. Please understand this. Okay, this property, please understand that if you have a DFA, then when the language will be infinite, if you have a DFA, let's assume you have a DFA D, then remember LD will be infinite. LD will be infinite if and only if there is some loop. There is at least one loop in the DFA from initial state to some final state. If there is at least one loop in DFA from initial state to some final state. From initial state to some final state. Okay, is this clear? So remember, the language actually will be infinite. For DFA, the language will be infinite. When can you say the language will be infinite? When this type of situation happens, that from the initial state, this is your initial state, from the initial state to some final state. Okay, to some final state. This is one of the final states. Okay, this is some final state. This can be any final state. Okay, so remember, this is some final state. Now, the language will be infinite. When the language will be infinite, the language will be infinite if and only if there is some loop from initial state to some final state. On the way, there is some loop. Okay, there is some loop here. Means on the way there is some loop. On the way there is some loop. Is this clear? Okay, on the way there is some loop. So this is what I'm saying, that the language of DFA will be infinite if and only if there is some loop in the DFA. Okay, in the DFA on the path from initial state to some final state. I can say on the path from initial state to some final state. I hope you understood. Is this clear? Let me know. Is this point clear? This is a very simple point. If you have a DFA, then the language will be infinite if and only if there is some loop on the path from initial state to some final state. Means if this type of situation is there, from initial state to some final state on the path, if there is some type of loop, there is some kind of loop, okay, then in this situation, the language will be infinite. Now, what I am going to do? Now you try your best. Okay, try to make sure there is no loop from initial state to any final state. Okay, let's make sure that you don't bring any loop. Is this clear? Please tell me what I'm doing. Did you understand? See, the DFA has 4 states and DFA is accepting a string of length n minus 1. The number of states, this is basically n, and the length of this, you can see the length of W is basically n minus 1, that is 3. Okay, now what I will do? I will try to make sure that there is no loop in the DFA on the path from initial state to any final state. Okay, so if I want to do this, then what I will have to do? Tell me. I want to do this. So this is your string. Your string is basically A, B, A. This is your string. You will start in the initial state. Now remember, this string is accepted. Please understand, this string is accepted. Because this string is accepted, so this is final state or not? This last state is final or not? Yes, this is final. Yes or no? Because this string is accepted. We are assuming this string is accepted. Okay, this W is accepted by DFA. This is accepted by DFA. So because this is accepted by DFA, so this state, this last state will be final state. Okay. Now make sure there is no loop. Make sure there is no loop. Tell me, if I do this Q0, okay, means on this A, if I'm going from Q0 to Q0, then there is a loop, yes or no? If I do this, please understand, if I do this, there will be a loop. If I do this, there is a loop. Okay, I got a loop. Loop found. Okay, loop found implies infinite language. Yes or no? Is this understood? Please tell me. So you can see, if I do this, means from state Q0, from the initial state on symbol A, if I go to initial state, then there will be a loop. It's like this. Basically, you got this type of loop you got from Q0. This type of loop you got. Yes or no? You got this type of loop on the way to Q final. So I hope you got it. So you got a loop, so the language will be infinite. So this cannot be Q0. Do you agree with me? Do you agree with me that this cannot be Q0? Because I don't want any loop. I don't want any loop. Okay, no problem. Let me take Q1 because I have 4 states. I have 4 states. Yes or no? I already have 4 states. Is this clear? Okay, accepted by DFA. In this DFA, there are total 4 states. You have total 4 states. So I can use Q1. There is no problem. I can use Q1. Okay. Now you tell me one thing. If I use this Q0 here or this Q1 here, either Q0 or Q1, then will I get a loop if I use Q0 or Q1? Here, if I use Q0 or I use Q1, then will I get a loop if I do this? If I do this, yes, again I will get a loop. Yes or no? Again I will get a loop. So if you do this, again loop found. Again loop found. Okay, loop found means again infinite language. But I want to make sure that I don't get infinite language. I want to make sure I don't get infinite language. So I cannot do this also. Let me use some Q2 and let me use this Q3. This Q3 is the final state. Let's assume. Okay, Q3 is the final state. So now, can I say I have avoided all the loops? Okay, see, very interesting thing is coming. Please understand. Very interesting thing is coming. Can I say I have avoided all the loops? Can I say I have avoided all the loops? So can I guarantee that there is no loop? Can I say there is no loop? Can I say there is no loop on the path from initial state to some final state? On the path from initial state Q0 to some final state, that is your Q3. Can I say? Please tell me. This is an interesting question. So can I say there is no loop? Can I say there is no loop? Can I say there is no loop? See, there will be a loop. There will be a loop because it is a DFA. It is a deterministic finite automata. See, there will be a loop. Notice. It's something like this. This is the initial state. On A, you are going to Q1. On B, you are going to Q2. On A, you are going to Q final. Okay, Q3. Now notice, this is a DFA. So in the DFA, in the deterministic finite automata, from every state, on every symbol, you must make a transition. Yes or no? From every state, on every symbol, you must make a transition. Agree with me? Do you agree with me? This is a DFA. Because this is a DFA, so from every state, on every input symbol, you must make a transition. Is this clear? Because this is a DFA, deterministic finite automata. So from every state, On every input symbol, you must make a transition. Tell me where you will make a transition from Q3. Just make a, this is what I'm telling you. Make transition from Q3. Now, make transition from Q3. First of all, you tell me, is this necessary? Is this mandatory that Q3 must have transition on A, B? Is this mandatory? Tell me. In the DFA, in the deterministic finite automata, is this mandatory? Is this necessary that this final state Q3 must have some transition on A, B? Yes, that is the definition of DFA. So now you make transition from Q3 on A, B. Where you will make? Where you will make? If you make a transition. Now where you will make? Wherever you make, you will get a loop. Okay, whatever you make. For example, if you make transition like this, you got a loop. I got a loop. If I make transition like this, I got a loop. Whatever you do, you will get a loop. Are you getting my point? This is the interesting proof. I hope you understood. See, whatever you do, you will get a loop. Notice, you got a loop. Is this clear? I hope you understood. See, you got a loop. Whatever you do, you will get a loop. Okay, you can do whatever you want, you will get a loop. Is this clear? If you do like this, you got a loop. Is this clear? Please tell me. So, that is the final thing. So, you can see our final conclusion is that if DFA has n states and you are accepting some string of length n minus 1, then language must be infinite. Is this clear? Is this clear? Please tell me. DFA has n states, and if you accept some string of length n minus 1, then the language will be infinite. LD must be infinite. Must be infinite. And I hope you understood. I hope you understood the proof. Did you understand the proof? Please tell me. Because if you want to avoid the loop from initial state to any final state, if you want to avoid the loop, then remember at the end, from the final state where you will make a transition. See, this is the simple point. I hope you got it. What I am trying to tell you. Very simple point that from the initial state, this is your string. Your string W is A1, A2, A3 and so on, AN minus 1. Okay, you are accepting this string. So at the end, you are in the final state. Okay, you are accepting this string. This string is accepted. So at the end, you are in the final state. Initially, you are in the initial state. Now, if you want to avoid the loop from the initial state to any final state, from the initial state to this final state, if you want to avoid the loop, then what you need to do? You need to use all the new states. Okay, keep using new states. Keep using new states. You keep using. Okay, but if you keep using these new states, if you keep using, then this will be what? Okay, so for example, let me start with, yeah, so this is Q0, so this will be n minus 1. So you can see there are total n states. So you have consumed all the n states. Is this clear? You have started from Q0 to Qn minus 1. So you have consumed all the n states you have consumed. Now you can notice, after doing this, where you will make a transition from QF, yes or no? Where you will make a transition from QF means from here where you will go on A. Just notice, from here where you will go on A and where you will go on B. Is this clear? Where you will make transition on A, where you will make transition on B. Because if you make transition to any state, you will get a loop. Is this clear? If you make transition to any state, you will definitely get a loop. Very simple. So from Q0, okay, you can go to Q final, that is fine. Okay, Qn minus 1, this is your final state. But now, if you make a transition on A to this state, let's assume you are making a transition on A to this state, then you got a loop. Then we got a loop. See, this loop we got. Yes or no? We got this loop. Is this clear? Please tell me. So we got this loop. This is the loop. Okay. So the language must be infinite. So that's it. Is this clear? So in this type of situation, the language LD must be infinite. Okay. So is this point clear? Please tell me, is the proof clear? Is the proof clear? So let me give you this statement. Okay, I am giving you this statement. This is a very nice, beautiful statement I am giving you. And that is, if you have a DFA D with n states, there are n states. Okay, DFA D with n state, there are n states. So DFA D accepts infinite language. Accepts infinite language if and only if. This is a if and only if statement. Okay, DFA D accepts infinite language if and only if D accepts some string of length greater than equal to n. If and only if D accepts some string of length greater than equal to n minus 1. Okay. Now remember, the same statement I can also say greater than equal to n length. That is also fine. The same proof will work. Yes or no? Is this clear? The same proof will work. Notice one thing, what I am telling you. See, if DFA accepts, if DFA D, there is a DFA D with n states, there are n states. Okay. Now I am saying that if DFA D accepts some string of length n minus 1, then also language will be infinite. Accepts some string of length n minus 1 or more. Okay, is this clear? So you can see, if DFA D accepts some string of length n minus 1 or more, then language will be infinite. Will be infinite. Yes or no? So this statement is, we have already proven. This proof we have already seen. Already proven. This proof we have seen. We have seen proof. Okay. Now the same statement, remember, of course, if the DFA accepts a string of length n, then also the same proof will work. Yes or no? Same proof will work. I can say the same proof will work. I hope you understood. So remember, if the DFA is accepting some string of length n or more, then also the language will be infinite. And if the DFA accepts some string of length n minus 1 or more, then also the language will be infinite. Okay, is this clear? To every student, is this point clear? This is a beautiful question. Please tell me. Let me know. Is this clear? So remember, option A is also correct, option B is also correct. Option A, option B, they are correct. Okay, if DFA accepts some string of length n, DFA is accepting some string of length n, then the language will be infinite. Of course, yes. Similarly, if the DFA accepts some string of length n minus 1, then also the language will be infinite. So both the statements are actually true. Option A, option B, both are true. What about NFA? What about NFA? Let me know. What about NFA? See, let's see this option number D. Is this option number D correct? Please tell me. Let's see option number D. NFA is accepting some string of length n minus 1. Then can I say the language will be infinite? Tell me. There is a NFA and this NFA is accepting NFA with n states. There is a NFA with n states and this NFA is accepting. This NFA accepts some string of length n minus 1. Some string of length n minus 1. Of length n minus 1. Then what you can say? Then can you guarantee LD will be infinite? Then can you guarantee LD will be infinite? Then LD infinite, can you guarantee? Please tell me, can you guarantee LD will be infinite? Let me know. Can you guarantee LD will be infinite? The answer is no. You can easily give a counter example. For example, okay, let me give you counter example. You can take n equal to 2. So 2 states you have. Now consider this NFA. Just consider this NFA. Okay, you can consider this NFA. Is this clear? Just consider this NFA. Now you can notice the language is also finite. The language actually is A, B. This is the language. But you are accepting a string of length n minus 1. Is this clear? Please tell me. Okay. So now did you understand that NFA does not need transition from the final, this last state? Yes or no? Now, are you getting the point? Can you connect the dots? Please tell me. Can you see what happened in the case of DFA and what is happening in the case of NFA? See, in the case of NFA, it is not mandatory that this state has transition on every symbol. It is not mandatory that this state has transition on symbols. Is this clear? So you can have missing transitions. In the NFA, you can have missing transitions, dead transitions you can have. So you can see, this is the idea. But in the case of DFA, from this state, you must have a transition to some other state. Or maybe from this state, you must have a transition to itself. Yes or no? So in the case of DFA, every state must have transition on every input symbol. But in case of NFA, you can have dead transitions. Okay, is this clear? So remember, in case of NFA, this is wrong. If NFA is accepting some string of length n-1, that does not guarantee that the language will be infinite. But even in the case of NFA, if NFA is accepting some string of length n, then the language will be infinite. Okay, then the language will be infinite. If NFA is also, okay, let me give you the proof. The proof is quite simple. So let me give you the proof for option C. Tell you the proof for option C. So basically there is a NFA with n states, and accepting some string of length n. Some string of length n. Now in this situation you can notice this some string, let's call it w. Okay, so this w you are basically accepting. This w is like this, a1, a2, a3 and so on, an. This is your w. Now NFA is accepting this string. NFA with n states accepting this string. So because you are accepting, so let me call it final. Okay, this will be the final state. Yes or no? The last state will be final. The first state will be initial. Yes or no? This will be the initial state. Okay, the last state will be final state. Now you can easily notice that some state must repeat. Yes or no? Because you have total n states. In this sequence, how many states will be there? Tell me. In this sequence, how many states will be there in this sequence? Please tell me. Because in this sequence, some state will be here, some state will be here, some state will be here, and so on. I can say this will be like n plus 1. Yes or no? Sorry, this will be like n. So total how many states are there? See, look at this sequence. In this sequence, there are total n plus 1 states. Right? There are total n plus 1 states. Okay. So you can say some state will definitely repeat because you only have n states. Okay. Some state will definitely repeat because in this sequence you have n plus 1 states. In this sequence, NFA is going through n plus 1 states. But NFA has only n states. So some state will repeat. Yes or no? I can say some state will definitely repeat. So some state will repeat. Some state repeats. I can say some state will definitely repeat. For example, let's assume this state is repeating Q1. Let's assume this Q1 is repeating. Okay, let me assume this Q1 is repeating. Okay, just assume for a moment that this Q1 is repeating. If this Q1 is repeating, because some state will repeat. If this Q1 is repeating, then you can notice what I can do. If this Q1 is repeating, then what I can do? I can repeat this any number of times. Okay, yes or no? This A2, A3 I can repeat any number of times. Because this Q1 is repeating, it's like there is a loop. See, some state will repeat. So there is a loop. Please understand, there is a loop. Okay, it's like this. From Q0, you are going to Q1. Okay, now there is a loop. On Q1, there is a loop on A2, A3. There is a loop on A2, A3. Okay, yes or no? There is a loop on A2, A3. On this A2, A3. There is a loop on A2, A3. Okay, yes or no? And then finally, after some time, you are going to final. So you can see this I can take any number of times and the language will be infinite. Yes or no? The language will become infinite because this loop you can repeat any number of times. So the language will become infinite. Okay, this is A to A3. This is not A2 comma A3. This is A to A3. This is one thing, A to A3. This is not A2 comma A3. This is A to A3. This is single thing, A to A3. So there is a loop basically. There is a loop. You can notice. Please notice. There is a loop from initial state to some final state. From initial state to some final state. On the way there is a loop. There is a loop. So because of that the language will become infinite. Okay, is this clear? So this is the proof. I hope you understood. So for this question, which statement will be correct? Which statement is true? So the answer will be A, B, C. These are the correct statements. Okay? Is this clear? Please tell me. Is this understood? A student is saying that regarding which option? See, a student is saying this blind partner. A student is saying, sir, here for option B, consider a DFA with two states where starting state is the final state and all transitions in all states go to state 2. What's wrong with that? The wrong thing is you are not accepting any string of length n minus 1. Is this clear? See, you have made a very nice comment, but please notice the option number B is saying, option number B, see what this option number B is saying. Look at this option number B. Focus on this option number B. That D is accepting some string of length n minus 1. D is accepting some string of length n minus 1. Okay, if you do this, basically what you are saying, let me tell you, you are saying that take a two-state DFA, make this final state, and from this DFA, all the transitions will go to Q1. See, the problem is you are not accepting any string of length n minus 1. Look at this DFA. This DFA is not accepting any string of length n minus 1. There is no string of length n minus 1 which you are accepting. Okay, so very good. So that is the reason I can say this example will not work. Is this clear? This example will not work. Anyway, we have seen the proof. Did you understand the proof? Let me know. So finally, let me tell you, this is a beautiful question. Okay, one day this question will definitely come in the GATE exam. Okay, someday in the future years, definitely this question, or I can say similar type of question will come in the GATE exam. Because many students, they by heart that, see, this is fine, but this option B is interesting. Let me tell you, this option B is interesting. This option B is actually interesting. So in the GATE exam, someday they can ask you this question. Because this option B is actually interesting and this is true also. Option B is true also. Only option D is false. All the remaining options are true. Okay. So definitely someday this type of question, similar type of question will definitely come in the GATE exam. Okay. Now let's move on. Now let's solve this question. This is another very simple question. Which of the following statements is or are false? The question is asking for false statement. Let A and B be sets of languages over some fixed alphabet sigma with A subset of B. If A is closed under some operation, then can I say B is closed under same operation? Please tell me. See, the question is saying that A, B are set of languages. Okay, what are A, what are B? They are set of languages. Please notice. A, B are set of languages. Here, let A, B be set of languages. Okay, such that A is subset of B. So remember here, in the option A, the A, what is A? That is basically set of languages. That is not a language. A is not a language. That is set of languages. And what is B? That is also set of languages. Is this clear? They are set of languages. And the question is saying A is subset of B. Means every language is in A, that is also in B. Okay, every language in the set A, that is also a language in the set B. Okay. Now the question is saying, if A is closed under some operation, then can I say B is also closed under the same operation? Can you give me a counter example? Please give me a counter example for option A. Give me a counter example for option A. Anyone? Anyone want to give me a counter example for option A? Option A is saying if A is closed under some operation, then some operation P, then B is also closed under operation P. Remember, A is subset of B. Okay, A is subset of B. Yes, very simple. You can consider that A, this is A, this is B, this is A, this is B. Now you are saying that if A is closed under some operation, then B is also closed under some operation. No, you can assume that A is your regular languages and B is your CFLs. Yes or no? Is this clear? Basically, in the counter example, take A is set of regular languages, set of all regular languages. Okay, is this clear? And take B, set of all CFLs. And which operation? And what you take? Operation what? And you take operation. Which operation should I take? Please tell me. Which operation should I take? You take operation intersection. You take operation intersection. Yes or no? Intersection operation you can take. Is this clear? Please tell me. So this is the counter example for option A. For option A, this is the counter example. Take A equal to set of all regular languages. A is set of all regular languages. B is set of all CFLs. Every regular language is CFL. So you can see A is subset of B. Yes or no? Every regular language is CFL. Every regular language is CFL. So set of all regular languages, that is subset of set of all CFLs. That you already know. Now you can easily see. You can take operation equal to intersection. You can see this set of regular languages, this set A, this is closed under intersection. But this set B, this is not closed under intersection. Okay. Is this clear? Please tell me. So very simple. This statement is actually false, right? Option A, that is actually false. Did you understand the counter example? You can take the operation equal to complement also, no problem. Yes or no? Regular languages means I can say this set A, this is closed under complement, but this set B, CFLs, this is not closed under complement. So you can take operation equal to complement also. You can take operation equal to intersection also. But the point is, you got a counter example, right? Yes or no? So option A is false. What about option B? What about option B? If B is closed under some operation, then can I say A is closed under same operation? If B is closed under some operation, then can I say A is also closed under same operation? Give me a counter example. B is closed under some operation, then can I say A is also closed under same operation? Which counter example you will give me? Yes, I can give you this counter example. You can assume set of DCFLs as set A. Okay, set A is basically DCFLs. You can assume that A is your DCFLs and B is your CFLs. Is this clear? You can assume B is CFLs and A is DCFLs. You can notice every DCFL is CFL. So set of DCFLs, that is subset of set of CFLs. So you can see A is subset of B. Yes or no? A is subset of B. Now you can notice if B is a subset, if B is closed, what is the counter example for option B? For option B. So you can see which operation I should take. Please tell me. Give me some operation under which CFLs are closed but DCFLs are not closed. Give me some operation under which this set B is closed. This set B is closed under this operation, but this set A is not closed. So that operation, for example, you can consider union operation. Yes or no? You can consider union operation. You can consider. So this statement is also false. Okay. What about this next statement? For all set A, B, if A, B are non-regular. Okay. Remember A, B, they are non-regular languages. Now they are languages, not set of languages. They are languages. So for all set A, B, if A, B are non-regular, can I say their intersection will be non-regular? Can I say non-regular intersection will be non-regular? Option C. A, B, they are non-regular. A is also non-regular language. B is also non-regular language. Now, can you guarantee their intersection will be non-regular? what will be their intersection? A intersection B. Let me give you two examples. Okay, for example, consider this example. A is non-regular. So what I can do? I can take A power n, B power n greater than equal to 0. Okay. B is also non-regular. So let me take, B is also non-regular, right? B is also non-regular. So let me take A power n, B power n plus 1, where n is greater than equal to 0. Now, what will be A intersection B? Please tell me. What will be A intersection B in this situation? A is A power n, B power n is greater than equal to 0. B is A power n, B power n plus 1, n is greater than equal to 0. The intersection is phi. There is nothing common. Yes or no? So you can see this is regular. A intersection B is regular. This is actually non-regular. This is also non-regular. So A comma B are non-regular, but their intersection is regular. Yes or no? Now I can give you another example where the intersection will be non-regular. I can give you example where the intersection will be non-regular. Okay, this type of intersection I can give you. For example, what I can do? A power n, B power n, where n is greater than equal to 0. This is non-regular. That you already know. Okay, this is non-regular. Another language I can give you, that is like this. A power n, A power 2n, B power 2n. Yes or no? Where n is greater than equal to 0. This is also non-regular. Now, if you take their intersection, what you will get? If you take their intersection, you will get B, which is non-regular. Okay. So remember, non-regular language, they are not closed under intersection. Is this clear? They are not closed under intersection. Is this clear? I am just giving one example. A student is asking, sir, why did you take B power n plus 1? I am just giving you one example. Of course, you can give me many examples. For option C, A comma B are non-regular. They are non-regular languages. Okay, now I can give you many examples. For example, take any non-regular. Okay, let's take any non-regular. Take any non-regular. Please notice, take any non-regular language. Okay, now the complement also will be non-regular. So just take B equal to A complement. The complement of non-regular is non-regular. If you have a non-regular language, the complement will always be non-regular. Okay, the complement of non-regular will always be non-regular. Remember, the complement of non-regular language will always be non-regular. So you can see, you can take any non-regular language, whatever you want. Now, this A complement, you can take B equal to A complement. That also will be non-regular. That also will be non-regular. Now, what the intersection of A comma B? Please tell me. What the intersection of A comma B? Remember, B is A complement. So what the intersection of A comma B? That will be phi, which is regular. Yes or no? Which is regular. Is this clear? So remember, remember, intersection of non-regular languages may or may not be non-regular. Is this clear? So remember, non-regular, intersection non-regular, this may or may not be non-regular. This may or may not be non-regular. May not be non-regular. Is this clear? Please tell me. Intersection of non-regular languages that may or may not be non-regular. But remember, the complement of non-regular will always be non-regular. Okay, the complement of non-regular will always be non-regular. So this option C, that is actually false. What about option D? Please tell me. What about option D? The set of all decidable languages is closed under operation of taking subset. Subset operation means if L1 is decidable and L2 is subset of L1, then L2 is decidable. This statement is also false. Under subset operation, no class of languages is closed. See, no class of languages is closed under subset operation. Let me give you for option number D. In the option number D, basically the question is saying if L1 is decidable. Okay, L1 is decidable. Okay, L1 is decidable. L2 is subset of L1. L2 is subset of L1. Then can I say that L2 will be decidable? Then can we guarantee? Then can we say L2 will be decidable? Then can we say L2 is decidable? Tell me, can I say L2 will be decidable? See, L1 is decidable. Decidable means recursive. Okay, decidable already means recursive, right? So you can see L1 is basically recursive. Now L2 is subset of L1. This is already given to you. Then can we say that L2 will be decidable? Can I say L2 will be decidable? The answer is no. Can you give me a counter example? Can you give me a counter example? Yes, of course I can give you a counter example. Take this L. Okay, let me give you a counter example. Counter example is like this. Take this L1 equal to sigma star. Can I say this is decidable? Can I say this is decidable? See, L1 equal to sigma star. Sigma star is regular. Every regular language is recursive. So, every regular language is decidable. Yes or no? Decidable means recursive. Every regular language is decidable. So, you can see L1 is sigma star. Sigma star is decidable. Decidable means recursive. Yes or no? Language is decidable when it is recursive. Decidable means recursive. Please understand. This is your, see, every finite language, notice, every finite language, these are the finite languages. Every finite language is regular. These are the regular languages. Every regular language is DCFL. Every DCFL is CFL. Every CFL is CSL. Like this, like this, like this. Okay, like this. You can see. There is CSL. Okay, and finally, you can see every CSL is recursive. So this is your decidable. Notice. This recursive is decidable. Okay, so this is your recursive. Every recursive, the another name for recursive is decidable. The another name for recursive is decidable. Decidable is another name for recursive. Is this clear? Okay, the another name for recursive is decidable. Okay, and you can see every recursive language is RE. Another name for RE is recognizable. Okay, every recursive language is RE. The another name for RE, recursive enumerable language, the another name is recognizable. Is this clear? So this is the chart. So you can easily see. Now take this sigma star. This is regular. Every regular language is recursive. Decidable means recursive. Okay, every CSL is recursive. Every regular language is DCFL. Every DCFL is CFL. Every CFL is CSL. Every CSL is recursive. Is this clear? So you can see this L1. This is decidable. Now I can give you, see, every language is subset of sigma star or not? Please tell me. Every language is subset of sigma star or not? Please tell me. Every language is subset of sigma star or not? See, if your sigma is A, B, every language is subset of sigma star. Every, whatever language you take, please notice, every language, notice every language, RE or not RE, RE or not RE, every language, whether you take RE language or whether you take not RE language, every language is subset of sigma star, right? Yes or no? RE language or not RE language. You can take RE language, you can take regular language, you can take non-regular language, you can take RE language, not RE language. So basically every language is a subset of sigma star. Okay, is subset of sigma star. Sigma star is regular. Sigma star is regular. Every language is subset of sigma star, that you already know. This is the definition of language, that every language is subset of sigma star, whatever language you take. Okay, now notice what I'm doing. Now notice what I'm doing. See what I'm doing. So you take this sigma star, this is your L1. You take this L1 equal to sigma star, and this is your regular language. Because this is regular language, so every regular language is DCFL, every DCFL is CFL, every CFL is CSL, every CSL is recursive. So this is recursive also. Recursive means decidable. Recursive means decidable. So this L1 is actually decidable. Okay. Now you can take a subset which is not RE. See. Okay. See. Assume. Okay. Take any non-RE language. See. Take any non-RE language. Take any. Please notice. Take any undecidable language. Take any undecidable language. That is your choice. Take any undecidable language. Okay, let's call it L2. Can I say L2 will be subset of L1? Please tell me. See, take any undecidable language. Take any undecidable language L2. Definitely L2 is also subset of sigma star. Yes or no? L2 is subset of sigma star. Yes or no? You can see this is decidable. Sigma star is decidable. But you are already taking L2 is undecidable. Yes or no? You have already taken L2 as undecidable. Is this understood? Please tell me. Is this point clear to everyone? Let me know. Is this point clear to everyone? You can see sigma star is regular. Now take any undecidable language. That is your choice. Feel free to take any undecidable language. Undecidable means not recursive. Undecidable means not recursive. Not recursive means undecidable. So take any not recursive language. Okay, take any not recursive language L2. Now automatically you can see L2 will be subset of sigma star because every language is subset of sigma star. Now you can see sigma star is decidable and this L2, this is subset of sigma star, and you have already taken L2 as undecidable. So you can see subset of decidable can be undecidable, agree or not? Subset of decidable can be undecidable, right? Correct. Agree with me? Let me know. Is this clear? Please tell me. I hope you understood. So this is the simple point. Okay. So remember, you can take any undecidable language, that is your choice. For example, you can take L2 equal to, you can take any undecidable language. For example, you can take set of Turing machines, set of Turing machines, set of Turing machine where M is Turing machine, where M is Turing machine and LM is equal to sigma star. Okay, or maybe LM is equal to something, maybe LM is equal to phi, right? So you can easily see this L2 is actually undecidable. Yes or no? This is actually undecidable. Okay, but you can see L2 is actually subset of sigma star. Every language is subset of sigma star. Okay, so you can see this undecidable language, this is actually subset of sigma star which is decidable. Okay, so this is the counter example. Counter example is you take L1 equal to sigma star and L2 equal to any undecidable language. Any undecidable language. Any undecidable language. You can take any undecidable language. Okay. So I hope you understood. So remember, L2 will be a subset of L1. Okay. I hope you understood. So tell me one thing. I'm asking you, which class of languages is closed under subset operation? This is an interesting question. You tell me, which set of languages, I can say which class of languages is closed under subset operation? Which class of languages is closed under taking subset, under subset operation? Please tell me. Give me one class of language which is closed under subset operation. Can you give me? Can you give me one class of language which is closed under subset operation? Anyone? Can anyone give me one class of language which is closed under subset operation? Can I say regular languages are closed under subset operation? Tell me. Can I say regular languages, like set of regular languages? Can I say regular languages? Please tell me, can I say regular languages are closed under subset operation? No, of course not. Of course not. Okay. For example, the same example you can take L1 equal to sigma star. This is regular. This is regular. But now you can take its subset. Okay, now you can take its subset. Take its subset. For example, you can take this subset A power n, B power n. This subset you can take. This is non-regular. Yes or no? This subset is non-regular. This subset is non-regular. Okay, see, L1 equal to sigma star. This is a regular language. But you can take subset of sigma star. You can take subset which is non-regular. So regular languages are not closed under subset. Is this clear? Can you tell me some class of language which is closed under subset operation? Anyone? Which class of languages is closed under subset operation? Let me give you some options. Okay, some options I am giving you. First option, set of finite languages. Next option, regular languages. Next option, DCFLs. Next option, CFLs. Okay, next option CSLs, next option recursive languages, which is your decidable languages, next option RE languages, which is your recognizable languages, next option not RE languages, next option not RE languages. Okay, next option non regular languages, next option non CFL languages, next option infinite languages. Okay, infinite languages. Are you getting my point? Next option non regular languages. Anything did I miss? So, this is the question. Tell me the answer. Now let me know. Please tell me. Which of them is closed under subset operation? Which of them is closed under subset operation? So, let me tell you. Only finite languages are closed under subset operation. Okay. No other thing is the answer. No other thing is the answer. No other thing is the answer. Is this clear? Only the finite languages are closed under subset operation. Notice one thing. Which class of languages is closed under subset operation? The set of finite languages. The set of finite languages. The set of finite languages. Okay, this is closed. Why? Because if you have a finite language, see, if you take any finite language, this L is any finite language, can I say its subset also will be finite? If L is any finite language, can I say its subset also definitely will be finite? Please tell me, please tell me. L is any finite language. Any finite language. Can I say its subset also will be definitely finite? A subset also will be definitely finite. Yes, of course. Subset of finite language will always be finite. Is this clear? What about infinite languages? Please tell me. What about infinite languages? Let me know. What about infinite languages? Please tell me. What can you say about infinite languages? Can I say, if L is infinite language, can you guarantee its subset will definitely be infinite? If L is infinite language, then can you guarantee that subset of L will definitely will be infinite? Can I say? Can I say the subset will be infinite? Subset will be infinite? The answer is no. Okay, the answer is no. For example, sigma star is infinite. Yes or no? Sigma star, that is infinite language, but its subset phi is a subset of sigma star, that is finite. Yes or no? That is not infinite. Is this clear? Please tell me. Did you understand? Let me know. Okay, see, now I am asking some questions back to back. You tell me the answer. Give me this type of situation. Okay, give. Okay, let's quickly give. Give where L is non-regular. Where L is non-regular language. Please take your copy pen and give me where L is non-regular language and L2 is subset of L and L2 is regular. Can you give me? Means, did you understand? Give me where L is non-regular and give me a subset. Give me a subset. Give me a subset which is regular. Which is regular. Can you give me? Please tell me. Let me know. Can you give me this type of language where L is non-regular but it's a subset, the subset of L, that is regular? Yes, I can give you, for example, very simple, a power n, b power n greater than equal to 0. This is non-regular. Okay, and I can give you L2 which is 5, which is regular. Yes or no? L2 equal to 5, which is regular. Is this clear? Please tell me. Yes or no? So very simple. Now give me L which is not RE. L which is not RE. Give me L which is not RE and give it subset which is RE. Give me L which is not RE and give me subset which is RE. Give me a language which is not RE language, but its subset, for example, its subset L2 also you give me which is RE. Yes, of course, I can give you L equal to set of Turing machines, where Turing machine M is a Turing machine, where M is a Turing machine, and LM is equal to phi. Okay, LM is equal to phi. So this is actually not RE. This language is actually not RE. Okay, this is unrecognizable. Now you can take its subset, which is phi, which is recognizable, which is regular, which is RE. Yes or no? Is this clear? Please tell me. So you can see this language, this L, this language is actually not RE, but it's a subset you can take, it's empty subset you can take, which is RE. I hope you are getting my point. Okay, is this clear? Please tell me. So you can do whatever you want. For example, give me RE language, whose subset is not RE. Whose subset is not RE. Give me RE language whose and its subset L2 which is not RE. Yes, of course, I can give you, for example, L equal to sigma star. This is RE language. Yes or no? This is RE language. And I can give you L2 equal to any not RE language. Okay, L2 equal to any not RE language you can take. Any not RE language. You can take any not RE language. Because your L1 is sigma star. Okay, and every language is subset of sigma star, right? Every language is subset of sigma star. So, like this. I hope you understood the complete analysis. Please tell me, is this point clear? Let me know. So, this is your question. Did you understand this question? Please tell me. So, I have provided the complete analysis of this question. I hope you understood. Is this question clear to everyone? Particularly option number D. So, remember, option number D is saying if L1 is decidable and L2 is subset of L1, can you guarantee L2 will be decidable? This is actually false. Why this is false? This is actually false. Tell me why this is false. Tell me why this is false. Very simple. You can take L1 equal to sigma star. Okay, see what you can do. You can take L1 equal to sigma star. So just take L1 equal to sigma star. Of course, sigma star is decidable. Decidable means recursive. Okay, decidable means recursive. So of course, sigma star is decidable means that is recursive. And this L2 you can take any undecidable language. Any undecidable language. Any undecidable language. Okay, because remember, you can take any undecidable language. Why? Because every language is subset of sigma star. So this L2 will be subset of L1. Yes or no? Every language is subset of sigma star. So you can see L2 is basically subset of L1, where L1 is decidable. L1 is decidable, but L2 is undecidable. You have taken L2 as undecidable. You have taken any undecidable language. So remember, this D is actually false. Is this clear? So for this question, which statement are false? So all the statements are false. A, B, C, D. All the options are false. Is this clear? Please tell me. Let me know. Please tell me. Is this understood? Let me know. Chandan is saying, sir, I got 30th rank in this All India Mock Test 3 and I am not from Go classes. Is my rank good one or do I have to improve? Like I made some silly mistakes. See, there is always improvement. Even if you get the first rank, there is possibility of improvement always. That will always be there. Okay, if you are getting first rank, does it mean that you don't have to improve? You always have to improve. Till the last day. Your GATE exam is on the 10th. Yes or no? On the 10th February, you have the GATE exam, GATE Computer Science exam. Till that day, you have to improve. Keep improving. Okay, so please don't be demotivated or don't be over motivated. Yes or no? Don't think that you have understood everything and don't think that you are not good. Okay, see, you can always improve. Keep improving. Till the last day, keep improving. Whether you get All India rank 1, whether you get rank 1 or rank 100 does not matter. Just keep improving. Okay, see, you have done some silly mistake. You are saying that you have done some silly mistake. So next time, take care. Don't repeat those silly mistakes. Make some new silly mistake. You can make some new silly mistake, but do not repeat any silly mistake. Okay, once you have done some silly mistake, don't do it again. Okay, once you have done some silly mistake in Go classes All India mock test, don't do that same silly mistake in the GATE exam. Okay, so because of silly mistake, you can lose a lot of marks. 4-5 marks you can lose because of silly mistake, and that will make a lot of difference in the rank. Okay, so keep improving with a positive mindset. Okay, yes or no? Keep a positive mindset that I will keep improving. Whatever mistakes I did in this, I did some silly mistakes, I could not manage the time. Okay, so this concept was not clear. But basically just analyze the test, and whatever mistakes you did, don't repeat those mistakes, just do some improvement. Okay, so with a positive mindset. Okay, so just have a positive mindset and keep improving. You are doing very good. If you are getting 30th rank in Go classes All India mock test out of 1000 students attempted this All India mock test 3. Okay, out of them you have got All India rank, I can say, sorry, rank 30. That is a very good, excellent. You should keep going. So for this question, the answer will be ABCD. Okay, let's move on now. Now let's solve this question. This is another beautiful question. Particularly option C is very good. Okay, let's solve this question. You can see below is a drawing graph representation of a binary relation R over a set of elements A, B, C, D, E, F. So set of elements are given to you A, B, C, D, E, F, and this is a diagram representation of binary relation R. Is this clear? This is diagram representation, graph representation. This is a graph representation of binary relation R on these elements A, B, C, D, E, F. Okay, so you have this set of elements which is A, B, C, D, E, F. This is the set of elements, and you are defining a relation R. This relation R you are defining on this set of elements P. This is what you are doing, and this diagram is telling you what is the relationship. So basically, for example, you can see A is related to A, right? Yes or no? You can notice C is not related to C. You can see there is no self loop. You can see F is related to F. You can see F is not related to E. You can see C is related to D. You can see D is not related to C. Yes or no? C is related to D. There is arrow from C to D. This simply means, what this arrow means? This arrow means C is related to D, but D is not related to C. You can see here C is related to B, but you can notice B is not related to C. You can notice A is related to B, B is related to A is related to C. Sorry, A related to C, C related to A. For example, here you can notice that this means A related to C. Okay, this means A related to C. And what this means? This means C related to A. Okay, so you can see A related to C, and this means C related to A. So like this. So first you understand the question. So this is a diagram or graph representation of the binary relation R, which is defined on these elements A, B, C, D, E, F. Okay. Now the question is saying which of the following first order logic statements is or are true. Some first order logic statements are given to you. Which of them are is or are true? So let's see option number A. Focus on option number A. Okay, is this true or not? The option is saying for every element in this set, means for every element you are saying that if it is related to itself, then there is some element to which it is related. See, very simple point. You are saying that for every element you are saying, what you are saying? You are saying that if this element is related to itself, then there is some element to which it is related. If X is related to itself, then there is some element to which X is related. This statement is definitely true. Okay, why? What is the reason? You can see for every element you can notice that this will be true. For every element, you can take any element. For every element, what will happen? For every element, what will happen? This statement that if X is related to X, then there exists some element, to whom X is related. Okay, there exists some element to whom X is related. Now you can notice this. For every element, actually this is true. Why? Tell me, is this true for A? Is this true for A? Yes, it is true for A, because A is related to A, and there exists element to which A is related. A is related to A. Here also A is related to A. Okay, see, for example, let me tell you, if you take x equal to A, then which y you can take? Which y you can take? There exists a y, right? There exists a y. So let me tell you, if you take x equal to A, if you take x equal to A, for every element you need to check, yeah, right, yes or no? For every element you need to check, will this be true or not? So if you take x equal to A, you are checking for x equal to A. You can see A is related to A. Yes, A is related to A. So there must be some element to which A is related. There must be some element to which A is related. Yes, you can see, for example, A is related to C. Okay, if I take B, if I take x equal to B, then you can see, if I take x equal to B, I am checking for x equal to B, then you can notice B is related to B. Yes, this is true. Okay, B is related to B, this is true. So there must be some element to which B is related. There must be some element to which B is related. Yes, that element is B itself. That element is B itself. Okay, because there must be some element to which B is related. That element can be B itself, right? Yes or no? No problem. That element can be B itself. Okay, for C, you can see C is not related to C, right? You can notice C is not related to C. So this is false. False implies anything is true. Yes or no? You already know that false implies anything. False implies anything. False implies anything. This is actually true. Okay, so remember, for C, I can say this statement. Let me call this statement. Okay, let me call this statement beta, or maybe let me call this statement something called gamma, maybe whatever. Okay, so let me call this gamma. So you can see, for this actually I can simply say gamma is true. For this C actually gamma is true. Is this clear? So for this C I can just simply say gamma is true. This gamma is true. Okay, what about D? For D, you can see D is related to D. So there must be some element to which D is related. D is related to D. Let's check for D. Okay, if x is equal to D, then you can notice D is related to D. Then there must be some element to which D is related. Yes, D is related to D. For E you can take E. Okay, or for E you can take C also, no problem. For E you can take C also. For F you can take F. So you can see that option A is actually true. Yes or no? Option A is true, because for every element in this diagram, for every element in the set, in the base set, if that element is related to itself, if x is related to x, then there is some element to which x is related. Yes or no? You can notice. Is this clear? And remember, for this element C, this has become false because C is not related to C. So this has become false. False implies anything will be true. Okay, I hope you understood. So this is your option number A. So option number A is true. Option number A, that is true. What about option number B? Please check option number B. Let me know what about option number B. Option number B is saying there exists some element such that for all elements x is related to y. Okay, there is some element which is related to every element. See option B. Okay, let's look at option number B. Option number B is basically saying that there is some element x which is related to every element. X is related to y. Okay, it's like this, that there is some element which is related to everyone. Okay, there is some element which is related to, for all y, this x is related to y. Okay, so do we have such element? You can see F is not related to everyone, D is not related to everyone, A is not related to everyone, B is not related to everyone, C is not related to C, C is not related to F. So you can see there is no such element, right? So this is actually false. This is actually false. There is no element which is related to everyone. There is no element which is related to everyone. For example, C is not related to C. Yes or no? A is not related to D. D is not related to A. B is not related to A. E is not related to A. F is not related to A. Okay, so I hope you understood. Is this clear? So option B, that is false. What about option number C? Let's focus on option number C now. Please tell me, what about option number C? Option number C is saying there is some element for which this must be true. Okay, option number C is saying that there is some element. There must be some element. There must be some element for which this must be true. For which this, for all y, x or y. Okay, for which this must be true. This must be true. Okay, so remember, there is some element for which this must be true. Okay, let's call it. Now let me call it S. For example, for a moment, let me call this box S. Let me call this S. Now you can notice, do we have some element for which S is true? There exists some element for which S is true. Is there some element for which S is true? Yes. You can take C. Yes or no? You can take C. You can take x equal to C. You can take x equal to C. For this C, this will be true. Okay, for this C, you can notice C or C will be false. Okay, you can notice false implies anything that will be true. False implies anything that will be true. That will be true. Is this clear? Yes or no? Please tell me. Is this clear? Very simple. So notice that option C is saying there is some element for which this internal thing is correct. There is some element for which this internal expression is true. So yes, you can take C. For C, this internal expression will be true. Okay, there should be some element. There must exist some element for at least one element. So you can take x equal to C. For this element, what will happen? This internal expression will be true. This internal expression, this is going to be true because C is not related to C. So this will be false. False implies anything is true. So you can see, very simple. So option C is actually true. What about option D? Finally, what about option D? Option D is saying that for every element, there is some element such that x is related to y. See, option D is saying that for every x, there is some y such that x is related to y. What it means? It means everyone is related to someone. Okay, means for everyone there is someone. For everyone there is someone. For everyone there is someone. For this there is someone. For this there is someone. For this there is someone. Okay, for everyone there is someone. So this is what this option D is saying. So can I say for everyone there is someone? Yes, of course. Yes, of course, for everyone there is someone. For example, see, notice, this is x. X is A, B, C, D, E, F. Okay, this is a y. This is a y. Y is A, B, C, D, E, F. Can I say for everyone there is someone? Yes. For A there is A. For B there is B. For C there is a, for C I can say for C there is D. For D there is D. For E there is E. For F there is F. So for everyone there is someone. So yes, this statement is also true. So finally, which statements are true? Tell me, which statements are true? So we have seen this statement was true. Okay. So what we have seen this statement was true. This statement was true. This was true. And I think only this statement is actually false. So the question is asking which is true. So the answer will be A, C, D. This will be the answer. So this was a good question. Let me know. Is this understood? Please tell me. Please tell me. A student is asking, by default, can we assume x, y are different? No. X is also in the domain. Y is also in the domain. Is this clear? X is also in the domain. Y is also in the domain. They can be same. They can be different. Don't make any assumptions. Just because you are writing x, y, it does not mean they are different. Okay, this is x, this is y, they must be different. No. Okay, is this clear? Please tell me. Is this understood? Is this question clear to everyone? So remember, x is also in the domain, y is also in the domain. Your domain is set P, set A, B, C, D, E, F. This is your domain. X is also in the domain, y is also in the domain. They can be same, they can be different, they can be anything. Okay, a student is asking, sir, in the GATE exam, can all the options be true for MSQ? Yes, of course. For MSQ, one option can be correct, two option can be correct, three option can be correct, four option can be correct. Okay, so very simple. Is this clear? Let me know. Anyone has any doubt? A student is asking, can we relate option number C with drinker paradox? No, we cannot relate. Ankit, we cannot relate with drinker paradox because You can see in the option number C, if you notice the option number C, see, look at the option number C, you don't have null quantification there. Okay, there is no null quantification. You can watch the null quantification video I have uploaded on the GoClasses YouTube channel. The null quantification lecture I have already uploaded. You can check it. So this option number C, this is not related to drinker paradox. Don't confuse. Because in the option number C, you can see after the implication, the expression that is given to you, that has a free variable x. So that is not a null quantification. Okay, that is not a null quantification, because you can see for all y, x are y. So there is a free variable x here. Okay, after the implication, in the option number C, after the implication, there is a variable x. Okay. Any other doubt? So is this question clear to everyone? Please tell me. Let me know. Okay, let's move on now. Let's solve this question. This is another good question. A very beautiful question. Assume that the following graph is labeled graph. Means every vertex has a unique label. In this graph, let's assume every vertex has a unique label. For example, let me call it vertex A, vertex B, vertex C, vertex D, vertex E, vertex F. This is the graph that is given to you. In how many ways can we color the following graph? This graph is given to you. In how many ways can we color it? The question is asking, in how many ways can we color it with 6 colors such that no two adjacent vertices have same color? Is the question asking for chromatic number? Please tell me. Is the question asking for chromatic number? The question, is it asking for chromatic number? See, the question is not asking for chromatic number. For this graph, the chromatic number will be 4 only. Yes or no? You can easily check. Actually, the chromatic number will be 4. What is this? This is basically chromatic number. Okay. So the chromatic number for this graph will be 4. But the question is not asking the chromatic number. The question is actually asking that how many ways are there such that you can color this without giving same color to the adjacent vertices. You cannot give same color to the adjacent vertices. No two adjacent vertices have same color. Okay. In how many ways can you color it? In how many ways can you color it? With these 6 colors. 6 colors are given to you. Okay, with these 6 colors, in how many ways can you color it? This is what the question is asking. Okay, so let's solve it. This graph is given to you. You can see. This graph is given to you. Okay, this is your vertex A, vertex B, vertex C, vertex D, vertex E, vertex F. Okay, this graph you have. Now let's see. So you need to use these colors, right? Which colors you need to use? You need to use, there are total 6 colors are there. You can easily see. Okay, R, G, B, whatever. It does not matter the names. W, Y, M. These are the colors. Okay, red, green, blue, white, yellow, magenta, something. Okay, so you can see these 6 colors you have to use. Okay, now let's see. Tell me, for this vertex, how many choices I have? Just tell me, for this vertex, how many choices I have? I want to give a color to this vertex. How many choices I have? To this vertex, I want to give a color. How many choices I have? Let me know. Please tell me. How many choices I have for this vertex number A. For this vertex A, I want to give a color. How many choices I have? Which color can I give to vertex number A? I am starting from vertex number A. Which color I can give to vertex number A? I can give any color. Yes or no? To this vertex number A, I can give any color. So I can say there are 6 ways. There are total 6 ways. Yes or no? There are total 6 ways. Let me give color number red. Let me give color number red. I am giving color number red. Okay. I have given color number red. Because remember, you can give any color to the vertex number A. I am starting from vertex number A. You can use any of the colors. So there are 6 ways for vertex number A. So let me give color number red. Now tell me, for vertex B, how many choices are there? For this vertex, how many choices I have? Please tell me. Can I use color number red? Can I use red color for B? I cannot use red color. So there are 5 ways. There are 5 ways, yes or no? Because I cannot use red color for vertex number B. I cannot use the red color. So there are only 5 ways. I have to use the remaining colors. G, B, W, Y, M. I have to use one of them. Yes or no? So let me use, okay, so remember I have to use some one of them. Okay, so let me use the green color. Let me give the green color here. Now you tell me, for vertex number C, how many ways are there? Tell me, for vertex number C, how many ways are there? To this vertex number C, which color I can give? Which color I cannot give? To the vertex number C, which color I cannot give? Just tell me that. To the vertex number C, which color I cannot give? I cannot give the green color. Yes or no? Because green color is already given to vertex number B. So I cannot give the green color to vertex number C. Yes or no? For vertex number C, I can use any color, but I cannot use the green color because green color is given to its neighbor, that is B. To the neighbor of C is B. So you can see, to the vertex B, I've given green color. So I cannot give green color to the vertex C. So for the vertex C, I can use any color. I can use red color also. Okay. So remember, for vertex number C, there are 5 ways. There are total 5 ways. Okay. I can give any color. For example, for this vertex number C, I can use any color. Okay. Let me use another, again, red color. I can use the red color again. So let me use the red color again. Now tell me, for vertex number D, how many choices? For vertex number D, how many choices? Tell me, for vertex number D, I cannot give red color to the vertex number D because this vertex C has red color. So I cannot give red color to the vertex number D. So again, there are 5 ways. I can use any color I want. For example, let me give blue color here. Let me give blue color here. So 5 ways for vertex number D. Now you tell me, how many ways for vertex number E? To the vertex number E, I cannot give red. I cannot give blue. To the vertex number E, I cannot give red comma blue. So there are total 4 ways. Yes or no? There are total 4 ways. To the E, I can give, for example, I can give white color. I can give. Okay, I can give white color. Now finally, you tell me, what about this? What about this vertex? This vertex. For this vertex, remember, you cannot use red color, blue color, white color. For this vertex number F, for this vertex F, you cannot use red, blue, white. So there are total 3 ways. I can use yellow color. I can use yellow color. Is this clear? So tell me, finally, what is the answer? Finally, what is the answer? What is the number of ways to color? What is the number of ways to color? Number of ways to color this graph. How many ways are there to color this graph? So that will be 6 multiplied by 5 multiplied by 5 multiplied by 5 multiplied by 4 into 3. Is this clear? Please tell me. So remember, your final answer for this question, the number of ways to color, how many ways are there to color this graph G? Okay, how many ways are there to color this graph G using 6 colors? Using 6 colors. So remember, how many ways are there? Number of ways to color this graph using 6 colors. That will be 6 multiplied by 5 multiplied by 5 into 5 into 4 into 3. Okay, can anyone tell me what is this answer? Anyone want to tell me what is this answer? Please tell me. Can anyone tell me what is this answer? So for this question, I think 9,000. Will the answer be 9,000? Just calculate. Okay, what will be the answer? So you can see, for example, this is 20. 20 multiplied by 30. This is 30. So this is your already 600. Yes, this will be 9,000, right? Yes or no? So the answer will be 9,000. So this was a simple question. Agree with me? This was actually a very simple question. Do you agree? And this is a new question for the GATE exam. This type of question has already come in the TIFR exam 3 times. In the TIFR exam, this type of question has come 3 times. Okay, so definitely this question will come in the GATE exam in future years. You can take my promise. Okay, in the future, in the GATE, This type of question will definitely come where they will ask you how many ways are there to color a graph. A graph is given to you, they will not ask you the chromatic number, they will ask you how many ways are there to color this graph. Okay, to color this graph, how many ways are there? Is this clear? Please tell me. Okay. A student is asking if vertices are not labeled, then what to do? Then there will be some complicated calculation will happen. Okay, because see, if vertices are not labeled, then some kind of complicated calculation can happen. Okay, because in that situation, see, if vertices are not labeled, can you tell me which two vertices they have no difference, like they have no difference if vertices are not labeled? If vertices are not labeled, then there will be some complications. Okay, for example, you can see if vertices are not labeled, then f comma e, basically they are the same vertices. Yes or no? F comma e, notice f d e, they are the same vertices. Yes or no? F d e, if vertices are not labeled, notice in this graph, if you don't label the vertices, then f d e, these three vertices will be the same vertices. Okay, so anyway, don't worry about that. This question, let me tell you, this type of question where you have to calculate how many ways are there to color a graph, the question is not asking the chromatic number, the question is asking how many ways are there to color the graph. So this type of question has come in the TIFR exam 3 times, and definitely in the future this question will come in the GATE exam also. Okay, so this was a simple question. Anyone has any doubt, let me know. Ankit is asking, sir, there can be this possibility that after coloring C, I choose F. You can do that, no problem. Okay, you can choose F first. There is no problem. The answer will be same. Ankit, see, first you color A, then you color B, then you color C, then you can color F, no problem. The answer you will get the same. Okay, so you can do basically that you can do. Okay, is this clear, Ankit? The answer will not change. The answer will be same. So very simple question. Now let me ask you a general thing. If you have k colors, see, using 6 colors, this will be the answer. Using k colors means you tell me. Okay, let me write it p g k. Okay, let me write it p g k. Please notice. This is your graph G. So this G is the graph and k is the number of colors. Okay, number of colors. K is the number of colors. You have k colors. Total you have 1, 2, 3 and so on. Total k colors you have. Okay, and this PGK, this means number of ways you can color the graph. Number of ways we can color the graph. We can color graph G using k colors. Okay, is this clear? Are you getting my point? I am asking that how many ways are there to color this graph G using k colors. Let's call it PGK. Let's call it. Means this is a number of ways you can color this graph. This graph G you can color using k colors. Okay. So now what will be PGK? So this is my question. What is going to be PGK? Did you understand this? Let me tell you, this PGK, this is called chromatic polynomial. Actually, this is called chromatic polynomial of graph G. Okay, this PGK, maybe you have heard this word PGK. Actually, this is called, let me tell you, this is called, what is this called? This is called chromatic polynomial of graph G. This is called chromatic polynomial of graph G. Chromatic polynomial. Remember, this is called chromatic polynomial of graph G. Is this understood? Chromatic polynomial of graph G with respect to k colors. Of graph G with respect to k colors. Please tell me, this is just a word. Did you understand what I'm telling you? Okay, so what is a chromatic polynomial if someone asks you? Means, see, the chromatic polynomial, basically what is that? Let me tell you. Don't worry, they will not ask you this directly, but I'm just telling you that number of ways is nothing but chromatic polynomial. Number of ways you can color a graph, that is nothing but chromatic polynomial. So if you have a graph G, and you have k colors, okay, if you have graph G and k colors, then in this situation, there is something called PGK. Okay, this PGK, what we call it? This PGK, we call it chromatic polynomial. We call it chromatic polynomial. Chromatic polynomial. And what this means? What this means, let me know. This means number of ways, very simple. This means number of ways we can color graph G. Number of ways we can color graph G with k colors. Number of ways we can color graph G. How many ways are there to color graph G with k colors? With k colors. Is this understood? Please tell me. Okay, chromatic polynomial, this simply means how many ways are there to color this graph. Number of ways we can color this graph G with k colors. For example, for this graph, what is PG6? This we have already counted. This is 9000. Yes or no? Is this clear? This is now 9000. We have already calculated. For this graph, what is PG6? That will be 9000. Is this clear? PG6 will be 9000, means using 6 colors, how many ways are there to color this graph? That will be 9000. Tell me, for this graph, what will be PG5? Tell me, for this graph, what will be PG5? Let me know. PG5 means there are 5 colors. Okay, please understand that there are 5 colors. 5 colors, which are those? Okay, you can call them maybe 1, 2, 3, whatever. There are 5 colors. You can call them 1, 2, 3, 4, 5. There are total 5 colors. Okay, you have total 5 colors. Tell me what is PG5? Let me know. Let me know what will be PG5. Please tell me. Please calculate. What is PG5? Let me know. What will be PG5 for this graph? Very simple PG5. See, to this vertex you can give any 5. There are 5 ways. There are 5 choices. There are 5 choices for this. I can give color number 1. Okay. Now there are 4 choices for this. There are 4 choices for this. I can give color number 2. Now there are 4 choices for this. There are again 4 choices for this. I can give color number 3. Yes or no? Is this clear? Now, for this, how many choices are there? For this F, how many choices are there? Okay, for this again there are 4 choices. Again there are 4 choices. I can give color number 2. I can give. Yes or no? For this, how many? There are 3 choices. And finally, for this there are only 2 choices. Yes or no? So finally, what is the answer? That will be 5 into 4 into 4 into 4 into 3 into 2. What that will be? Your final answer, that will be what? Let me know. Anyone? So it will be like, you can just calculate, right? Yes or no? This will be your PG5. This is going to be your PG5. Is this clear? Let me know. 5 into 4 into 4 into 4 into 3 into 2. Okay. I think you can calculate. I think that will be 1920. Okay. So you can just calculate. This will be 1920. Okay. For this same graph, you quickly tell me what is PG4. For this graph, what will be PG4? 4 means 4 using 4 colors. Yes or no? You can only use 4 colors. Okay. So PG4. Basically, how many ways are there to color this graph using only 4 colors? So for example, let's assume you have only these 4 colors you have. Okay, now you tell me how many ways? Very simple. For this vertex, there are 4 ways. For this vertex, there are 4 ways. For this vertex, there are 3 ways. Okay, yes or no? For this vertex, there are 3 ways. For this vertex, there are 3 ways. For this vertex, there will be 2 ways. And for this vertex, there will be 1 way. Right? Yes or no? So your answer will be 4 into 3 into 3 into 3 into 2 into 1. This will be your answer. This will be your PG4. Correct. So this will be 216. Okay, this will be 216. Now tell me what will be PG3. Tell me what will be PG3, anyone? PG3 using 3 colors. Okay, you can only use 3 colors. So what will be PG3? PG3 will be 0 because even chromatic number is 4. Yes or no? See, the chromatic number itself is 4. You need at least 4 colors. The chromatic number itself is 4. Yes or no? You need at least 4 colors. The chromatic number for this graph is 4. So number of ways you can color using 3 colors, that will be 0. Yes or no? How many ways are there to color this graph using 3 colors? That will be 0. Is this clear? Please tell me. So very simple. Now tell me what will be PGK. Now you are expert. So tell me what will be PGK. What will be PGK? Where K colors. You are using K colors. Okay, where K, you can assume K is greater than equal to 3. K is greater than equal to 4. Okay, K is greater than equal to 4. Okay, K is greater than equal to 4 because chromatic number for this graph is given to you. For this graph, the chromatic number is actually 4. The chromatic number, that is actually 4, right? Okay, so tell me what will be PGK. Anyone want to tell me what will be PGK? Please tell me what will be PGK. PGK will be your chromatic polynomial, right? Yes or no? PGK, that will be the chromatic polynomial. That is very simple. You can give K colors here. There are K choices. K choices for this. There will be K minus 1 choices for this. Agree with me? There are K minus 1 choices for this. There are K minus 1 choices for this. There are K minus 1 choices for this. There are K minus 2 choices for this. Agree? Agree. Yes or no? Please tell me. This question has become cakewalk or not? Please tell me. For you, this question has become cakewalk or not? Are you confident in the GATE exam if they give you some other graph, some graph they give you, some random graph they give you? Are you confident that you can easily find how many ways are there to color the graph? Please tell me. Are you confident? Let me know. Let me know. Are you confident now? This question has become cakewalk for you. This question has come in the TIFR exam 3 times. This will definitely come in the GATE exam in the future. Maybe in 2024, 2025, 2026. Definitely one day this question will come in the GATE exam. And Go classes students, they will be easily doing this. Okay, for Go classes students, this question has become cakewalk. Okay, I can give you any random graph I can give you. Okay, and you can solve it. Yes or no? So, what will be your PGK? Very simple. Very simple. You can see the answer will be K multiplied by K minus 1 power 3, K minus 2, K minus 3. So this will be your chromatic polynomial of this graph. Is this clear? This is the chromatic polynomial of this graph. This is called chromatic polynomial. This is just a name. This is just a name. This is called chromatic polynomial. Understood? This is just a chromatic polynomial of this graph. Okay? So, I hope you understood. So, very simple. Remember, for this graph, the chromatic polynomial means this graph that is given to you. This graph that is given to you. For this graph, remember, what will be PGK? Okay, where K is the colors. Where K is the colors. And where this PGK, this is called chromatic polynomial. The name is chromatic polynomial. And actually what this means? This actually means number of ways to color. What actually this means? This simply means number of ways to color G. Okay, this simply means number of ways to color G. To color graph G with K colors. With K colors. Okay. And remember, for this graph, your PGK, that is K multiplied by K minus 1 power 3, K minus 2, K minus 3. This is your answer for this graph. Okay, for this graph, this is the answer. I hope you understood. So, shall I give you one more graph? This is a TIFR question I am giving you. This is actually TIFR question. Okay, this is actual TIFR question. A, B, C, D. What is the chromatic polynomial? Please tell me. How many ways are there to color this graph? You just tell me what is PGR. Where R is the colors. You have to use R colors. Okay, so this is your PGR. That simply means number of ways to color this graph. Okay, that simply means number of ways. Tell me, quickly tell me what will be PGR. This is your chromatic polynomial. This is the chromatic polynomial. Yes or no? And this simply means how many ways are there to color this graph. This simply means number of ways to color G. To color G with R colors. Okay, so tell me quickly. For this graph, what will be PGR? Okay, find PGR for this graph. How many ways are there to color this graph? Just find PGR. What that will be? Now this has become cakewalk for you. You have become expert now. You have become expert. A, B, C, D. Okay, so let's see. How many ways are there for option for A? How many ways are there for A? Tell me. How many colors I can use? I can use any of the R colors. Yes or no? There are R choices. There are total R choices. I can use any color. I can use any color. Yes or no? I can use any color. Let me use red color. Okay, let me use red color. Now, for this, how many choices are there? Or you can directly take this. For this, how many choices are there? Tell me. For this one. For this, how many choices are there? There are R minus 1 choices. Yes or no? R minus 1 choices. Now you tell me. How many choices for this one? You cannot use red. You cannot use, for example, let's assume here you have given blue color. Here you have given blue color. Here you have given red color. Okay, here you have given red color. So remember, you cannot use red comma blue here. Okay, so you have only R minus 2 choices. R minus 2 choices here. Let me use some green color. Okay, let me use green color. Now, for this, how many choices are there? For this, there are R minus 2 choices. Yes or no? Because I can use green again. I can use green again. Okay, I cannot use red comma blue, but I can use green again. Right? Yes or no? I can give green color again. So very simple. So this is the final point. So what will be the chromatic polynomial? You can easily see. So that will be chromatic polynomial, means your PGR, that will be R multiplied by R minus 1 multiplied by R minus 2 whole square. Can you make it open? Can you open it? Can you open it? R into R minus 1, R minus 2 whole square. Okay, so can you open it? This is what you got. PGR equal to R into R minus 1, R minus 2 whole square. If you open it, what you will get? You will get R square minus R multiplied by R square minus 4R plus 4. Okay, if you open it, this will be R power 4 minus 4R cube minus, see, R power 4 minus 4R cube plus 4R square minus R cube plus 4R square minus 4R. So what you got? You got R power 4 minus 5R power 3 plus 8R square minus 4R. This was the option in TIFR. This was TIFR option. This was given in TIFR option. Okay, this was given in the TIFR option. Is this clear? Okay, so you can see R power 4. Let me know. Is this understood? Please tell me, is this understood? So you can see R power 4 and you can see minus R power minus 5 R power 3. Okay, so this is 4R square, 4R square, 8R square and minus 4R, right? Okay. So I hope you understood. So that's it. Is this clear? This complete analysis, is this clear? This is a template of question that you have done. Remember, this is not single question. This is a template of question. This is a class of question that you have done. You have become expert of a class of questions. Any question they can give you from this concept. They can give you any graph and they can ask you how many ways are there to color this graph using K colors. You can do that. Yes or no? So remember, this is not a single question. This is a class of question. This is a template of question that you have done. Okay. So thank you everyone. Now, I hope you loved it. I hope you loved this complete analysis. Okay. So the remaining questions we can do tomorrow. Okay. So thank you everyone. Let me know. Did you love this session? Let me know. Please press the like button. Can you do that? Please do that. So just press the like button. So see, in every question we are providing you the complete analysis for every question. Okay, in all the All India mock tests so far, you can see in every video solution we always provide you the complete analysis. Okay, so please press the like button. Please put a comment on every video. Please put a comment. You can put a small comment. You can put a small, large. Okay, just put a comment. Your comment will definitely help us reach more students, so that we can reach more students. More students will get to know about Go classes. Okay, because a lot of students, they don't know about Go classes. So they join some other institute and then they regret. Then they comment that, sir, I did not know about Go classes. Now I regret, but now I cannot do anything. Okay, I wish I knew about Go classes. So basically this type of comments you will find on the Go classes YouTube channel. So that is the reason we request you to please press the like button and please put a comment under any Go classes video that you watch. Whenever you watch a Go classes video, if you like it, okay, if you learn something new, if you love it, then please put a comment. Okay, so just please do that. It will help us. So this type of complete analysis we are providing you for every question, in every session, for every question, in every All India mock test. So we always provide you with the complete analysis. Okay, whenever we provide you some analysis, remember, you will feel that you have not solved only one question. You have solved almost 10-20 questions, or I can say a class of questions you have done. So each question is not a single question. Each question is a class of questions. Okay, I hope you loved this type of analysis. So the remaining questions we will do tomorrow. Don't worry. Ankit is asking, sir, please take function question. I will take it. Don't worry. Okay, I will take the part 2. This was part 1. Tomorrow I will take part 2. Okay, is that clear, Ankit? Anyone has any doubt in this session? Let me know. Do you have any doubt in this session? Please tell me. Please tell me anyone has any doubt in this session. So there are some questions remaining. Of course, many questions are remaining. So those questions we will take in the next session. Okay. If anyone has any doubt, you can let me know. Okay. So let me tell you one more thing, that if you want to attempt all 20 mock tests of Go classes, in the Go classes there are total 14 mock tests, and in the Gate Overflow there are total 6 mock tests. If you want to attempt all the 14 mock tests of Go classes, or if you want to attempt all the 20 mock tests of Gate Overflow plus Go classes, then you can enroll for this mock test package. Okay, this mock test package you can enroll. You can see this mock test package we have created. This mock test package you can enroll. Okay, the link I will provide in the description. You can check it out. The link is already available in the description. You can check it out. Okay, so I hope you go to ISC next year. These are some of the Go classes GATE 2023 computer science students who joined ISC Bangalore. They are currently, I think, they have done their first semester. Okay, so you can see now they are in the second semester of ISC, and these are some of them. Actually, there are 4 or 5 more students. So total you can easily see almost more than 10 students they joined ISC Bangalore last year from Go classes. Okay, in ISC Bangalore more than 10 students went from Go classes. So, and similarly in IIT Bombay, IIT Guwahati, IIT Kanpur, in every old IIT, you will find at least 10 students in all the old IITs. At least 10 students in every old IIT and ISC you will find from Go classes. In ISC Bangalore itself, there are more than 10 students. I think 10 or 12 students are there in ISC Bangalore from Go classes. So I wish you go to your dream institute, ISC Bangalore or IIT Bombay, okay, any dream institute, IIT Delhi. So I wish you go there, okay. And let me tell you one more thing. If you are GATE 2025 or 2026 aspirant, if you are preparing for GATE Computer Science 2025 or 2026, then you can join Go classes GATE Computer Science complete course you can join. So enrollment have already begun. You can join this course. So let me tell you that enrollment has already started. Okay, so already started. You can join Go classes GATE Computer Science complete course. You can join. You will get extra validity. You will get 1 year plus 2 months of extra validity you are getting. Okay, so if you want to prepare for GATE Computer Science, for the best preparation, let me tell you, for the best preparation of GATE Computer Science 2025 or 2026, this GATE Computer Science complete course you must join for your best preparation. Okay. If you are GATE DA student, then you can join GATE DA course. Okay, you can join GATE DA complete course. You can join. Okay, so if you are a GATE DA student, you can join this. The link is in the description, so you can check it out. Okay. So please share your comment. Please put your comment and please share your feedback in the comments. Okay. Thank you everyone. Thank you so much. If anyone has any doubt, you can ask. Let me just see. Okay. So thank you everyone. See you tomorrow in the part 2. All India Mock Test 3 Solutions Part 2. Okay.